as everyone starts to trickle into today's session, just a reminder as we are gonna get started soon, to please mute yourself as you come in if you are not one of the speakers or conveners or asking a question, and keep yourself muted. And if you want to ask a question at any point during the session, to please either put it in the chat or use the raise hand feature and wait until a convener calls on you. But welcome everyone to today's morning session. We have a great lineup of talks for everyone that I will show right now. So today's session is all about shoreline crossing science, and the conveners are myself, Helen Janiszewski, Lindsay Worthington, Patrick Hart, and Moscow Tominaga. And again, just to reiterate, a huge thanks to Casey Adderhold for all the work that she's been doing for organizing this whole symposium. She's been a true hero these last months. So just again, a round of applause for Casey for everything that she's doing. So today we've got a lineup of 4 talks focused on science results from various shoreline crossing experiments that have happened recently. Our speakers are Anne Sheehan, Adrien Arnulf, Colton Linner, and Jim Garrity. And then in the middle of this session, we have a panel discussion that is how to build an amphibious experiment and instrumentation panel and discussion, focusing on past experiences with designing and running large-scale amphibious experiments, as well as an overview of some instrumentation facilities for marine geophysics. So with that, I'm going to stop sharing my screen, and I'm going to now turn it over to Anne Sheehan, who is a professor at University of Colorado Boulder, and she's going to be talking to us about shore crossing seismic tomography at the Hikurangi Margin in New Zealand. Take it away.
Great, thanks very much. Yeah, so today I'm going to be talking to you about a shoreline crossing experiment offshore the Hikurangi Margin in New Zealand. And I'm going to be focusing on 2 recent tomography papers that have just, they're in press and submitted from the Hobbits experiment. And I'd like to thank the conveners for organizing the session, and also the conveners of the whole workshop. I'm really looking forward to this. I've enjoyed the parts I've seen so far. Again, my name's Anne Sheehan. I'm at University of Colorado Boulder. I'll be showing a lot of the work of my collaborators, Jenny Nankai and Jefferson Yarse. And there are actually many collaborators, too many to list. And there are additional experiments going on or have recently happened offshore Hikurangi as well. So there's just a wealth of literature coming out now. It's a very exciting time. So the Hikurangi Plateau is subducting beneath the North Island of New Zealand, and it's actually it's an oceanic plateau. Recent papers suggest that it started as part of a large igneous province that included the Ongtong-Java Plateau, the Manahiki Plateau, and formed the Cretaceous, and then it rifted and moved to the south, subducting under the Chatham Rise, and then more recently it's been subducting westward underneath the Australian plate, underneath the island of New Zealand. So on the right, to get your bearings a little bit, we're going to be focusing kind of on the northeast tip of New Zealand. And here we have the town of Gisborne, and our study area is offshore here from the trench. And since it's shoreline crossing, we're also including GeoNet land stations in this region of northeast New Zealand. So on this plot, the red are contours of slow slip events that have happened. So the slow slip events are kind of earthquakes that take a couple weeks to happen. So things like GPS and seafloor pressure sensors can pick them up, but seismometers don't really see them. Also marked here in gray are some regions of subducting seamounts. So there's evidence from magnetics and from seismic reflection. And in down dip of them, there are some high reflectivity zones that have been imaged with seismic reflection. And then this is a lens reflectivity zone. So there's a hypothesis that these seamounts are pushing some sediments in front of them as they subduct and causing these reflectivity zones that are interpreted as potentially zones of trapped fluids and high pore fluid pressure, which might be the cause of the slow slip events or related. So slow slip events, again, they're slow motion earthquakes, take a couple weeks to happen. And there have been a number of them happening offshore Gisborne, New Zealand, and here they're shallow. So they offshore, or with Cascadia, the slow slip events are deeper, but in this region they're quite shallow. In the southern Hikurangi Margin, some of them are deeper. And so part of our study was to try to get a better handle on these and try to capture them offshore, as well as do imaging to help resolve what some of the physical properties are. And some of the motivation for understanding the subduction processes in these regions became really clear just last week when there were 3 earthquakes of greater than magnitude 7 in one day and within about 12 hours. And this shows where they are in a larger context with the Tonga Trench, Kermadec Trench, and then the Hikurangi Margin here. So it started out with a magnitude 7.3, which is about 2:30 in the morning local time. And then a few hours later, additional earthquakes resulting in tsunami warnings and evacuations. So the Hobbits experiment, so kudos to Susan Schwartz for the best acronym ever. Hikurangi Ocean Bottom Investigation of Tremor and Slow Slip. So it describes the experiment pretty well. So it was, the US part was funded by NSF and supported by OBSIP. And it was a collaborative project with USA, Japan, and New Zealand researchers and contributions. For example, we had a New Zealand ship in the deployment. The experiment included 24 seafloor pressure gauges that were deployed, 10 broadband seismometers, 5 short period seismometers, and a station spacing of about 6 to 22 kilometers. This shows where the instruments were and the different instrument types. So we do have kind of a heterogeneous network, which was actually, it was great to have all these other instruments, because if we had had only, say, the US instruments, it would have been a much smaller experiment. It would have been hard to resolve some of the features that were found. So we had ocean bottom seismometers from the Lamont Instrument Center. There were pressure recorders from Lamont and from University of Texas, and short period seismometers from ERI, Earthquake Research Institute, University of Tokyo. And there were also pressure sensors from Tohoku University and collaboration from Kyoto University. So the experiment was from mid-2014 to mid-2015. And this is about a 12-year time series of GPS at these 2 stations on land. And you can see the slow slip events, they happen about every 18 to 24 months, but they're not perfectly regular. But we were fortunate to capture this slow slip event during the deployment. And so Laura Wallace published a paper in Science using the seafloor pressure data to get to better constrain the slow slip event. The dashed line here shows where kind of the extent of the slow slip event. And then there have been subsequent papers, looking at different, looking at the data as well. So this is where the slow slip event was modeled to be along the plate interface, offshore, nearly going up to the trench, but we kind of lost resolution there. So again, in this talk, I'm going to be focusing on the seismic imaging aspects. And one of the hypotheses is that localized high pore fluid pressure produced by fluids from the dehydrating slab and sediments subducting contributes to slow slip. So this is a schematic from O'Day et al. Anyway, so with high pore fluid pressure, this reduces the effective stress, and it brings the system closer to the failure envelope. This is the same sort of physics that's involved with induced earthquakes. So you increase the pore fluid pressure and the normal stress goes down, and it brings things closer to failure. So fluid pressure can trigger the onset of seismic events and potentially slow slip events. So we're addressing this hypothesis using body wave, seismic velocity, and attenuation tomography. This shows some unfiltered seismograms from a magnitude 2.8 earthquakes that was recorded by the Hobbits Array and also by GeoNet land station. So this is a short period OBS. These were from Earthquake Research Institute, 3 components, broadband OBS, so it's unfiltered. So you can see that it's has a longer period response, and also a land station. So Jefferson Yarse, as part of his thesis, worked on earthquake locations and also seismic tomography with those earthquakes. So this is a figure showing some of his earthquakes. He found about 2,300 earthquakes during the 1-year period. They're colored by depth, and the size is by magnitude. So they were mostly small. Our magnitude of completion was about magnitude 1.5, both offshore and onshore. And the biggest earthquake was less than a magnitude 5. This is, since we had offshore instruments, we can get better offshore locations. This shows the difference between the GeoNet hypocenters and our hypocenters. So the events moved landward and shallower. So it suggests that the velocity model that GeoNet was using might be a little fast. So the seismicity was found to be mostly intraplate. The gray dots show the earthquakes. And this is where the slow slip is hypothesized to be, and a subducting seamount is in this region. And this is just a generic image of a seamount, just showing how sediments can flank them. So if you just kind of imagine that sort of thing, then subducting, that can be bringing a lot of fluids with it. And let's see. So we did seismic imaging of VP, Vpvs, attenuation, QP and QS, to map the lateral and vertical variations of material properties. This is a figure modified from Christensen, 1984, looking at how Poisson's ratio varies with pressure. So here is pore pressure. So as pore pressure increases, the Poisson's ratio increases. So this is a laboratory experiment. And just a reminder that Poisson's ratio and Vpvs are related. And so we'll be mostly talking about Vpvs. So when Vpvs goes up, that's the same as Poisson's ratio going up. And anyway, increasing pore pressure increases the Vpvs. So we selected a subset of events from the manually built catalog. So the best recorded events that had at least 8 arrivals and a azimuthal gap less than 180, and then use the TomoFD algorithm to invert for VP and Vpvs and also relocate the hypocenters. So this shows depth slice at 20 kilometers from the 3D VP image. And this shows lateral variations as the oceanic plate is subducting beneath the North Island of New Zealand. So at 20 kilometers here, we're seeing continental material, which is a slower wave speed than the offshore, which is seeing mantle. And the reds are slow and blues are fast. We look in cross section, so we can see the fast wave speeds of the subducting plate and can make an estimate of the crustal thickness of the subducting plate from the velocity gradient. And this also shows the earthquakes. So the earthquakes actually moved a little shallower in the with the 3D model. So they're a little closer to the interface, but still mostly intraplate. One of the more interesting features that's observed is if we look at Vpvs, several high Vpvs anomalies are found, and these might suggest areas of increased in pore pressure. So this is these are both images of Vpvs. So the reds are Vpvs of 1.85 and higher, and we've labeled them as HK1 and HK2. There were also lots of resolution tests that were performed to see whether these things were above the slab or below the slab, whether these were distinct or connected. And kind of grade this out here because the resolution tests suggest that this anomaly is mostly below the interface. So we see a lot of micro earthquake activity at the transition between the high Vpvs anomalies and kind of down dip of it. And this shows where the region of the slow slip event, which actually was along the plate interface. So it's in the region where the high Vpvs is located. So the next thing we did was looked at attenuation of the seismic waves from the local earthquakes. And this is work done by Jenny Nankai, and this was just, it's in press in JGR. So I think you can get it online now. So these are the equations used to model attenuation of seismic wave amplitude. So it's a lot more involved than picking travel times. We followed a method by Stocknick et al. Jeff Abers was involved with this as well. So in blue are the things that we want to solve for. So for each earthquake, which is by K, we want to solve for the moment and the corner frequency. And then for each path, so the kth earthquake to the jth station, we want to solve for T star, which is the ratio of travel time to quality factor. And the quality factor, this Q, is related to the loss of energy per cycle. So these are the equations. So we have an amplitude spectra from the jth station to the kth event, from the kth event to the jth station as a function of frequency. And we want to solve for these source parameters of moment and corner frequency, and also the T star, which is along the path. So we can linearize using just taking natural log of each side, and then let's see. Oh, this is just a reminder of what T star is, the equation for T star. So what we do is we do a grid search over corner frequency, and for each of these corner frequencies, we then invert for moment and T star, and then find the best fitting parameters. So this is what it looks like with the spectra. Here's this equation. things in blue are what we're solving for. We've got a noise spectra, so we only look at the data where a signal to noise is greater than 2. Blue is the P wave spectra. We also do this for S waves. Moment is related to the height here. And this is another place where having both onshore and onshore was helpful, because using the onshore, we found that with the broadband OBS, our estimates of moment were off, so that some issue with amplitude. And T star is from this curve. And then, so here's corner frequency, moment, and we do a grid search over a range of corner frequencies, solving for T star. Side effect corrections are really important. This is showing before and after side effect corrections for S waves on short period and broadband OBS. So what we care about is attenuation along the path, and not so much really close to the sensor. So for example, for this spectra, for this station, we see this resonance at around 8 hertz or so for all earthquakes, independent of path. And so when we correct for the side effect, we remove this features that are common to all earthquakes, regardless of the path, and get something that looks closer to a Brune spectrum. These are the tomography images, some depth slices. So where there are colors, those are places we have resolution. So low Q, which is high attenuation, is in red, and high Q, which is less attenuation, is in green. So this is at both QP and QS at 8, 16, and 24 kilometer depth slices. Also, the black shows the regions where Jefferson Yarst had high Vpvs, and then these show the seamount areas. So basically we have high Vpvs, high attenuation, low Q in 2 spots, offshore and onshore, that correlate with places where there is high Vpvs. So if we look in cross sections, this is QP and QS. This is a plate interface. Red is low Q. These hashed areas, it's a little hard to see. Those are the areas with high Vpvs, and these also correlate with low Q, this region here, which is at the kind of the toe of the slow slip event. Or no, at the region of the slow slip event has very low Q, it's like less than 50, and also high Vpvs. The blue triangles are the offshore stations, the green are the onshore stations. So the, having just one or the other just really limits you, and by having this shoreline crossing, you can really improve your resolution for the whole region. Pink shows where the slow slip event is modeled to be, and then blue, this little dash blue, shows where the seamount is modeled to be, projected to the interface. So Jenny explored the various causes, possible causes of seismic attenuation, explored temperature, serpentinization, scattering, and fluids. We don't think temperature is playing a role here. This is a temperature versus depth along the slab from a model by McCaffrey et al. And they're seeing temperatures in kind of the 50 to 150 degree C range, which would give you a pretty high Q relative to what we see. So at these depths, we don't think that's playing a large role. Serpentinization, This is from a study by Goswami and Barbeau, and they suggest that the thick serpentinized zone would be deeper than we're looking quite a bit up dip from that. So there could be some serpentinization along the slab that we just don't have the resolution to see. So then looking at scattering in fluids, there have been a number of controlled source experiments in the area, and they found some clear evidence of faults and also evidence for fluids from these reflectivity zones. This is from a paper by Bell et al. This is showing where the subducted seamount is and the high reflectivity zone in blue down dip from it. This is showing another high reflectivity zone. And then in map view, showing where these are located. Again, our study is kind of right here. There are clearly a lot of faults in the upper plate and the incoming plate. So the upper plate has a lot of thrust faults. So this is from an overview paper by Phil Barnes. And then the incoming plate has many normal faults. And there's a correlation with where we see low Q and where these highly faulted regions. So on the right-hand side corresponds to kind of the toe, and this region corresponds to kind of down dip of the seamount. So since I'm kind of running out of time, wrapping up. So we see low QP and QS on the order of 50 to 100, coinciding with high Vpvs anomalies. In particular, we're interested in this one that's down dip from the subducting seamount, and it's interpreted as fluids near the plate interface, down dip of the subducting seamount. We also see high Vpvs region and low Q region onshore. So this shows kind of the onshore stations and the offshore stations. And in the background is the VP image. So these results support the hypothesis that fluids exist on the plate interface and in the region of slow slip. And this really is just a snapshot of some work that I've personally been involved with, and there's just many, many more results coming out. There's ocean drilling that happened just a couple of years ago. So they're getting some direct measurements of the physical properties of the material. And we also, in this talk, I didn't examine temporal variations in these properties, something that Susan Schwartz, who's on the panel, has been involved with, and would also suggest looking at these papers by Warren Smith and Zoll, looking at temporal variation analysis in stress and anisotropy. And then just wrap up with just a shout out to some other Hikurangi presentations that are at this symposium this week and next week. So thank you very much. I'd be happy to take any questions. I've not been looking at the chat, but now I will.
Yeah, so if anyone has any questions, feel free to either raise your hand and I will call on you, or if you want to type your question out in the chat. It looks like Min Chen, you have a question?
Yes, thank you very much for the great presentation. And I'm interested in the local region that has high Vpvs ratio. Is that like a sedimentary layer or something else that is hydrated?
Well, we think that it includes a sedimentary layer that's hydrated, but also the basement that's highly faulted. And that provides pathways for fluids. So I don't think with our resolution that we could limit it to just the sediments.
Okay, so it's combination of
yes,
all these possibilities.
Yeah.
Thank you so much.
Susan Schwartz?
Hi, Anne, can you comment about, you showed, there's a gap in seismicity just offshore in the shallow, how that gap relates to the Vpvs, or
Yeah, actually, I'll just, not sure how, well, anyway, so the gap is, let me change, well, whoops, sorry. I've been doing Zoom all year, but I'm still uncoordinated.
Because, you know, one figure, it looked like the gap was between the two Vpvs low, but then in the cross section, it looked like there was a lot of seismicity.
Okay, here we go. So the gap is kind of right here. So there's a lot of seismicity, just kind of down dip of, can you see this?
Yeah.
Okay, yeah, there's a lot of seismicity down dip of the low Vpvs region. And the gap is kind of in between them.
So it's not necessarily, it's hard to interpret the physical parameters with the seismicity, is there?
Well, yeah, the gap is in, it kind of straddles the high and low Vpvs, that's correct. And yeah, this seismicity gap kind of here has been, it's been persistent. So if you look at, take a GeoNet catalog for, 15 years, it becomes even more clear that this region is fairly aseismic. So yeah, and our high Vpvs, it's kind of in between it, but it does overlap with it some.
Okay, so let's see. Anne Vassell, Christine Chelsea, and Yuhan have hands up. We're also a little bit over time. So Anne Vassell, can you go first, then Christine, and then Yuhan, I think you wrote your question in the chat. So then Anne, maybe you could answer in the chat afterwards so we can
okay.
Keep on time.
I'll do it after, okay.
Okay, but Anne and Christine, and then we'll move on.
Okay.
Okay, so actually I wanted to thank you, Anne, for this very nice presentation. And I know that there have been many studies recently in this area, and one of them is the control source EM data. So maybe I have the same question than Christine, I don't know, or maybe she can answer. But are your results in agreement with the CSCM data? Because there should be also anomaly associated with this high Vpvs.
Right. Well, yeah, Christine would be a better one to answer that. I think with the I did have a slide, but I took it out. But with kind of the on land part, there's EM that was published by Hess, and it correlates pretty well with the conductive regions. And then the offshore, yeah, Christine and Samer and Carrie Key, I think, have a paper in review. And I'll definitely take a look at Samer's presentation.
Yeah, I can just
from today. Yeah, Christine, you want to help me out?
Jump in and say that our profile doesn't actually extend as far as Anne was showing, but we do see the same high conductivity in a very heterogeneous 4-arc that sort of correlates more with what Jenny's results were, and seeing a lot of high attenuation zones in the upper plate. So we're, I guess, a little too far offshore of where Jefferson's high Vpvs was in the lower plate, but we do see high conductivity in the same. Yeah, this is a good figure for it, actually.
Okay. Yeah. So actually, yeah, that is interesting. This feature that Jenny sees, Jefferson doesn't resolve in his model, which is ironic because the VP or the velocity, we have a lot more rays, but they use different inversion algorithms with different criteria, and so Jefferson's model doesn't show this, unfortunately. But Christine, you're saying you have it's conductive here?
Yeah, we do have, I guess, more resolution and so we can see more localized zones of high conductivity. So it's not so dispersed throughout the entire 4-arc region.
Okay.
But I think Samer might show some of that next Tuesday. So stay tuned. But Anne, I did have a different question.
Oh, okay.
So I was wondering if you could maybe talk about or had some ideas as to why there is a gap between the high Vpvs in the slab, because if there's faulting in the slab, why isn't it faulted throughout the entire slab?
Mm-hmm.
So I was just wondering if you had some comments on that.
Yeah, no, that's a great question. Yeah, so I guess you're kind of referring to these two. Why isn't it continuous? I mean, I would, yeah, point to heterogeneity with, I don't know if there are other seamounts, but even though there is quite a lot of faulting along the subducting plate, it could be that there are regions that have maybe the cracks have closed due to the state of stress, or you know, dehydration reactions might be playing a different role at different pressure and temperature conditions, so that in this zone, it's the cracks aren't as open as these areas straddling it. But yeah, that's a great question. And we did do, yeah, with the sensitivity test, which I didn't show, we did, or Jefferson really did, looked at, you know, taking whether we have two things or not, and his tests suggest that these are truly separated.
Cool, thanks, and great talk.
Thank you.
All right, well, thanks again, Anne, for great talks to start us off with this session. Again, if anyone else has any additional questions, please feel free to just put them in the chat. But at this time, we're going to move on to our next talk by Adrien Arnulf. He is a research associate at the Institute for Geophysics at Jackson School of Geosciences, University of Texas at Austin. And the title of his talk is Anatomy of the Nankai Subduction Zone Revealed by 2 Decades of Active and Passive Seismic Data. So Adrien, share your screen and take it away.
So first I would like to, can everyone hear me, or I don't see the, oh, good. So first I would like to thank you, or to say thank you to the convener of this session for inviting me today. And in this presentation, I'm going to describe a large-scale seismic experiment that a team of us has been conducting over the past like 5+ years at the Nankai Trough. So the Nankai Trough is located in southwest Japan, and is a place where the Philippine sea plates subduct beneath the hammer plate at a rate of 4.1 to 6.5 centimeters per year, according to this subduction vector. And while there are numerous features from the incoming plate and overriding plates, I would like to, I would like you to pay particular attention to one particular feature, which is labeled KP here, which stands for Kumano Pluton. And it sits at the tip, or near the tip of the Kii Peninsula in Honshu. So in this next slide, here the red contour represents the strength of interseismic plate coupling along the plate interface. And this is derived from land and also offshore geodetic instrumentation. So this is the work of Yokota et al. In 2016, and it builds upon earlier work from Wallace and colleague in 2009. And the main results from those two surveys is that there is a strong reduction in coupling or locking, moving from the offshore region of Shikoku to offshore Kyushu. What's also interesting is that in this area, or in this region, there are also evidence of strong coseismic slip or megathrust earthquake that have occurred along the plate interface in those regions that are currently well coupled. So in 1944, we had the Tonankai magnitude 8.1 earthquake. 2 years later, we had the Nankaido magnitude 8.3 earthquake that ruptured a large area offshore Shikoku and the Kii Channel. And finally, in 1968, the Hikurangi Earthquake, which was a magnitude 7.8, ruptured a smaller patch just offshore the Bongo Channel. And the goal of this presentation here is to really relate processes that are occurring along the interface, as well as processes or hydration processes occurring within the downgoing plate with material and geometrical heterogeneities that have been derived from a large 3D tomographic experiments of this entire subduction system. And you might wonder how we build this tomography model. So we have combined like 3 different data sets. The first data set that we use is a large amount of OBS data. And over the past 20 plus years, there have been over 40 seismic surveys that have been conducted by Janiszewski of the offshore Southwest Japan. And this resulted in 110 seismic profiles. So those are the black lines shown here offshore. Among those 40 surveys, there were 16 ocean bottom seismometer surveys. And among those 16 OBS surveys, there were 5 regional grid deployments. And those regional grid deployments here consisted in 850 OBS deployments, which are represented by those yellow dots here or yellow circles. And what's interesting with those regional grids is that all OBSs, they were deployed on the seafloor prior to shooting. And so they offer not only online, but also offline data coverage. So as you can see here, so this is an azimuthal ray coverage map of the ray path that has been offered by those regional grids. And they offer really dense coverage of the entire FOAC region. The second data set is a data set of onshore offshore data. And this has been leveraged because over the same time period, NIED in Japan has been operating 2 of the densest network of onshore seismographs. So there is the F network, which is represented here by the blue dot, and the I network, which is represented here by the red dots. And what's very critical with those 2 networks is that all seismographs are located in deep boreholes, so often more than 100-meter depth. They provide a very quiet and low noise environment that has been very successful at recording shots fired offshore over the last 2 decades. And so we have recorded thousands of arrivals or millions of arrivals from those shot fire offshore. And the final data set that we have incorporated in our 3D tomographic inversion are arrivals from naturally occurring earthquakes that have been provided by the GMA catalog, so the Japan Meteorological Agency earthquake catalog. So we have used 150,000+ earthquakes, and this total this resulted in 1.8 million earthquake arrivals that have been added to the 1.6 million arrivals from onshore offshore data and 750,000 arrivals from OBS data. So the collected data set is more than 4.2 million arrivals. And we inverted all those data in this 3D volume. So it's a 800 kilometer long by 500 kilometer wide by 53 kilometer thick 3D volume. So in this next slide, so here I would like to show you the type of ray coverage that we obtained from those 3 data sets. So this is a movie, and it's for 15 OBSs and 5 INET stations. It represents less than 2% of the full data set. And what you can see is that the 3 data sets are very complementary of one another, and they provide dense ray coverage and cross ray path for the entire FOAC region down to the greatest depth of this model. So it provides very good constraint toward geometrical and material properties of this entire subduction zone. So now we'll move towards results. So in this next slide, I will show you a movie that shows trench parallel velocity section for the entire margin along this dashed black and white line here. So it will move towards shore. And I want you to pay particular attention to 2 regions, the upper mantle, which is located beneath those 2 dashed black lines. So the dashed black lines represent the top and the bottom of the downgoing oceanic crust for the Philippine sea plates. So the upper mantle, and the second feature I want you to pay attention is the Kumano Pluton. Again, it sits near the tip of the Kii Peninsula. and it will appear here next to the 500-kilometer mark. And please pay attention to the effect of the Kumano Pluton on the geometry of the downgoing oceanic crusts. So here we move landward. There is a low velocity anomaly in the upper mantle. Then we move towards the Kumano Pluton, which is this high velocity dense features, and it has a strong effect on the geometry of the Philippine Sea plate. So locally, the depth of the subduction zone here is 2 times greater than it is offshore Shikoku. So now for the next 3 slides, I would like to show you cross-section at hypocenter location of the 3 large historical earthquakes I mentioned earlier. So the first one is the 1944 Tonanki Earthquake. And what's interesting is that it nucleated near the edge of the Kumano Pluton. So near the edge of a very fast, dense body of material. And it propagated towards the east. Another interesting point is that the seismogenic zone in this region is characterized by this low velocity subduction channel that's surrounded by 2 layers of faster, denser material. Similarly, for the 1946 Nankai earthquake, it also nucleated on the boundary of the Kumano Pluton, so this fast, dense velocity feature, but this time it propagated towards the west. And what's interesting, again, for this big earthquake is that the seismogenic zone is also characterized by this low velocity subduction channel. And finally, in 1968, the Uganada earthquake, while it didn't nucleate in the vicinity of the Kumano Pluton, it also nucleated near like a fast and dense asperity. And again, the seismogenic zone is also characterized by this low velocity subduction channel. So you can ask me, like, what is the effect of this low velocity subduction channel on wave propagation? And to answer this question here, I'm going to run like a video that shows a numerical simulation of an explosive source that has been embedded at the bottom of the seismogenic zone, or down deep of the seismogenic zone. And what you can see here is that this low velocity channel acts as a perfect waveguide that traps the seismic energy towards and focuses the seismic energy towards the accretionary prism. And this has very strong implication because it will like involve like higher or stronger ground motion in the accretionary prism and could also result in a higher tsunami height. So like one key point from this like tomographic inversion is that by having a better knowledge of geometrical and material properties for the entire Nankai margin, we're able like to better, or we could probably better anticipate regions that are prone to strong ground motion. So now I'm going to show you another example. So I'm going to extract a slide along this profile, and along this profile, the slab has reached a depth 15 kilometers. So along this profile, everywhere the slab is, or the plate interface is at 15 kilometer depth. And I want to compare those velocities with residual failure gravity and slip rate deficits that has been extracted along the same 2D profile. But for the velocities here, what you can see is that the Kumano Pluton is a fast velocity body. Again, it's 6 kilometers per second or higher. In fact, this core is higher than 7 kilometers per second, so it suggests there is probably a mafic origin. And the main key results here is that when we move from offshore Shikoku to offshore Kyushu, there's a strong contrast in velocity. So the gradient in velocity here is twice higher than it is offshore Kyushu. Now, if we extract, again, the residual free air gravity and slip rate deficit from the 2 maps above, and we plot it along the same 2D transect, the main key observation is that where we observe like a strong reduction in velocities within the 4-arc region, we also observe a reduction in residual free air gravity and also a reduction in slip rate deficit or plate coupling. And also pay attention to like the beautiful link that we observe between, for example, the Kumano Pluton and the high free air gravity anomaly, or similarly here in the Tokai region, high residual free air gravity correspond to fast velocity within the overriding plates. So the model here is that when we're offshore Kyushu here, we're still within the outer 4-arc, which is which consists of under-consolidated crust. So VP is typically less than 4.5 kilometers per second, and it's more compliant than what we observe for the Nankai, Tonanki, and Tokai patch. So for those here, we're in the inner fork, and the crust is stiffer and less compliant. And what matters here is that the effective thickness of material that can accumulate elastic energy. And so if we plot the effective thickness, or like the thickness of material that has a velocity greater than 4.5 kilometers per second here, we see that it correlates very well with the slip rate deficit map. So it seems that material properties of the overriding plate are very important or very well correlated with plate coupling along the plate interface. So in the next few slides here, I would like to discuss the hydration of the downgoing Philippine sea plates. And to do so, I will extract a velocity profile along the Nantro-sized transect, which cuts through the Kumano Basin and the Kii Peninsula. And to introduce that region, here I'm using the P-wave velocity model from Nakanishi et al. In 2008, where the maximum penetration of the velocity model was just beneath the Moho. But the main features that I want to point out here are those sub-Moho reflectors here that are like picked in black that has been reported in that study. Another study that has occurred along the same transect is the work from Tsuji et al. In 2013. So those are, this is a depth migrated seismic profile of the outer fork. And the main features that I want you to look at are those red lines here, which mark like thrust and normal flow that cut through the entire oceanic crust. And the authors of this study infer that there are possible pathways bringing water down to the upper mantle, and there might be evidence, or there might be a serpentinized upper mantle in that region. But when you put it back into the context of our 3D tomographic model, this is what you get, and you see that it doesn't stretch the upper mantle, and we're left wondering, is the mantle serpentinized here? And so this is the P-wave velocity slide that we extracted from our 3D tomographic model, and you see that we observe a large low velocity anomaly under those fractures from Tsuji, and that low velocity anomaly is also capped by those reflectors that has been imaged by Nakanishi et al. In 2008. We can also like plot the isotherms from a 3D thermal model of the Nankai subduction zone that has been produced by G et al. In 2016. This is what you get. And from those isotherms, we can infer the stability field of some of the major hydrous phases in the upper mantle. So lizard light is typically stable up to 350 degrees. Then you have antigorite, which is stable between 300 and 650 or 700 degrees. And at greater depth, only chlorite is stable. So the main observation here is that this low velocity anomaly is mostly focused or mostly within the stability field of antigorite serpentine. So we can use empirical relationship linking P-wave velocity and volume fraction of antigorite serpentine to see how much serpentine is required to explain that low velocity anomaly. And so what we observe here is that we need at least 20% regionally, and at most locally 80% of antigorite serpentine to explain that low velocity anomaly. Another interesting fact here is that we can also plot the GMA earthquake catalog on top of this low velocity anomaly. And what we observe is that most of the seismicity is located within the lower half of this low velocity anomaly. And seismicity here might reflect antigorite destabilization with increasing temperature. Another interesting observation is from looking at thermomechanical numerical models. So this is the work of Nalibov et al. In 2013. This is to the exact dimension that, that they produced their model, so 150 kilometer by 50 kilometer. It looks like it was designed for this region, but it's not. Like, in fact, the plate age is higher than the Philippine sea plate in this location. But the main interesting point here is that here we're in the location of maximum bending, and this is where we expect fractures to reach the greater depth. So when we look at the location of those faults and where our low velocity anomaly is located, we see that they correspond very well. So now I would like to through the 3D model at a depth of 33 kilometers. I use this residual free gravity anomaly here to again like plot or like pick the contour of the Forak plutons, and those black lines here correspond to the faults that has been described by Tsuji et al. In 2013. So in fact, he has made like a map of those like fractures. And so this is the distribution of the low velocity anomaly relative to the Forak pluton. And what I want you to pay attention is when you look at the incoming plate vectors or subduction vector, you see that the low velocity anomaly sits just in front of the Forak pluton. And when you look at the ISO depth of the Philippine sea plate, you see that this is the location where the Forak pluton or the Forak pluton has the maximum effect on the subduction, on the geometry of the subduction zone. So here locally, the ISO depths are close from each other, so it means that the Philippine sea plate is subducting at a greater angle, so there is more bending, so it might explain why we have more fluids going down to the upper mantle. But we see that hydration is not correlated with age of the incoming plate. So in fact, it seems that it's only located in front of this high velocity dense asperity. So once again, we have proved that features from the overriding plate might have like great control on the geometry and material properties of the subduction zone. So this is another view from this low velocity anomaly, but I've plotted on top of it the GMA earthquake catalog. And this is a movie that shows you the distribution of all earthquakes in this region. So you see again that you have the Kumano Pluton that sits at the tip of Kii Peninsula, and this low velocity anomaly just wrapped around it. So if you crop like through this tomography model along like this red line, you will see that the Kumano Pluton is again these fast, dense features, and there is this low velocity subduction channel that we have discussed before, and it's on the boundary of that high velocity dense feature that like the 1944 and 1946 earthquake nucleated, and the ruptured region that are characterized by higher velocity. This next video here is really to show you like the beautiful tie that we have like between the P-wave velocity model and the residual free air gravity. So again, what you can see here is that where you have high residual free air gravity, you have a high velocity feature in the overriding plates. And when you have like, for example, a region of very low velocity, you have also like low residual free air gravity. And similarly in the Kumano basin, you have lower residual free air gravity that correspond to slightly lower velocity in the overriding plates. And you see that the tie is almost perfect on both sides of the Kumano Pluton, and there are even smaller features, so that's a little like path of higher residual free air gravity that correspond to a higher velocity path in the overriding plate here. And this is my summary slide. Again, I would like to mention that features in the overriding plate might be controlling to a greater extent that subduction zone. So again, like the Kumano Pluton here has a strong effect on the nucleation and probably the segmentation of the seismicity or the plate coupling within the overriding plate, and it also has like a very strong effect on the hydration of the downgoing Philippine sea plates. And I will thank you and accept any question.
Okay, does anyone have any questions? Either raise your hand or put something in the chat. Okay, Min Chen, go ahead.
It's a great talk. Again, I'm very interested in what you interpreted over there. However, there's one question regarding how you infer it is more coupled than it is not, only from the structural point of view. Do you have any geodetic study that shows you that part is also coupled or uncoupled?
Oh yes, the how can I stop? So this is this coupling map from Yokota. So this map that I compared the velocity structure with. So it's a plate coupling along the plate interface that has been derived from geodetic instrumentation, both like onshore but also offshore. So the offshore instruments are shown here by those squares. So the map that I always compare to is in fact derived from geodetic instrumentation. So again, that map has been derived from geodetic instrumentation. So this is the result from Yokota et al. In 2016. And that profile here is the value extracted along this gray line.
Okay, so if that's the case,
so I'm just comparing, yeah.
The structural, that kind of a bump or uplift of maybe some high velocity material that increase the coupling, is it the asperity that is needed for coupling or locking to happen?
What is needed is to have like fabrics that can accumulate like elastic energy. So you need something that's stiff enough so to accumulate like elastic energy. So if it's too loose, for example, offshore Kyushu, you won't have like as strong of a plate coupling.
Great, thank you so much. Thanks.
Okay, Jim Garrity.
Yeah, thanks, Adrian. That was great. Really amazing data set. So I was curious whether, and maybe you said this and I missed it, you found hydration, the main evidence for hydration sort of in that deeper, I think it was Antigrite field. Do you understand why you're not seeing the hydration in the shallower part of in the mantle between the crust and that deeper field where you do see it?
Yeah, I mean, this was very puzzling to us. And so I'm gonna go back to that slide. And I wonder if it has to do with like how fast, I mean, there is probably a temporal aspect with like how fast like antigorite versus lizardite will propagate. I don't know if it's something due to like those two major hydrous phases. But this is very interesting that it's not, that low velocity region is not located exactly under the moho.
Yeah, it's really interesting. Thanks.
Sean Gulick.
Yeah, thanks. Great talk, Adrian, as always. I'm curious about the low velocity zone and what your thoughts are on physically what it represents. It seems to, I guess it's a resolution issue, but it seems to be both where it could be subducting sediments and potentially hydrated ocean crust, or if you think it's just sediments, or what your thoughts are.
So you mean along the plate interface?
Yeah. Yeah, what's making up the quote unquote subduction channel where you're imaging it, do you think?
I mean, the truth is that here, I mean, like again, there is like a resolution aspect. We know that it's not part of the starting model, so it is built up like after like 60 iteration of travel time tomography. But there is still some smearing, like, so this might appear like thicker than it is in reality, but sure. I don't know. I mean, it's still fast. I mean, it's 6 kilometers per second. So at that time, it is like, it's a sediment that has been like, I mean, it's more like a rock than a loose sand at that point, yeah. But I don't know like exactly what it is made for. I mean, 6 kilometers per second will tell you that this is the velocity of many different rock types.
Yeah. Well, thanks.
Okay, and then we have a question from Spar Web in the chat. How common is it to see these giant plutons in the forearc?
Well, like, I mean, there is a big one here, but I don't think any like study has been conducted. Like, I mean, this is the first very like, dense tomographic study of any subduction zone. So I think like looking at residual free-air gravity would be like a good start. But again, I want to show you some things that from the starting model that was provided by Nakanishi-san. So it was a compilation of 2D tomographic model that has been stitched together. That was the starting model across the Kumano Pluton. And this is our final model. And you see that that was inexistent in the original model. So up until now, we knew that there was like a high velocity from little part of 2D transect, but I don't think the full extent of it was well understood. So I'm sure there are many other places on the planet where we could find like similar features.
Okay, we've got a couple more questions coming in the chat. We are in our break time though, so I think at this point, if people want to go and turn their cameras off for a bit and go get coffee or water, whatever time zone you're in, feel free to do so. But Adrian, is it okay if would you prefer to answer the questions just in the chat or still answer them verbally?
Oh, I can answer verbally. There is no problem with this.
Okay. Yeah. So everyone feel free to take a break if you want to at this point, but otherwise I'll just keep reading them from the chat. So Jenny Collier asks, could you expand a bit more on the deep reflectors? Do you see wide angle reflections from them in your data set?
So these reflectors, where is it? I suspect you're referring to the work of Nakanishi et al. In 2008. So we didn't process reflection yet, but if you look at this paper, this manuscript from Nakanishi et al. In 2008, yes, it comes from reflection that has been observed on a very dense OBS deployment. So for this tomographic model here, like I think the spacing between OBS was 1 kilometer, and they were able like to it was a type of migration of like reflectors from those OBS gather. So we didn't do it per se, but this is the work that they have done back in 2008.
Okay, sorry, perhaps I should have spoken. So thanks very much. So is that data set in your inversion, or are those OBSs in your data set?
Yeah, those OBS paths, every OBS line that has been fired offshore Nankai have been used. Okay, so we used every OBS. So those data, so if we look at the model, this model and this model, I mean, we use an inverted colors, but they should correspond almost perfectly.
But did you actually look
we have used
the reflections across your whole data set?
No, we haven't. Like, I mean, if you look at the data, so even for like onshore, offshore data, there are like, they are reflectors. So this is, for example, all the shot fired along this 8-way prime line that has been recorded by the KMT stations onshore. We picked the first arrival here, but we could also like pick like S waves. So we could also do the same thing for like a S wave model. But we could also like pick and migrate those data. So there are like thousands of those reflectors, receiver gather that could be migrated. So in fact, we could do a migration of the entire margin.
Wow, great, thanks very much.
Okay, and then Min Chen asked, is this a pre-constrained tomography?
Let me elaborate a little bit. Pre-constrained meaning that do you specify all these interfaces, for example, the Conrad interface and also Moho interface of the overriding plate and also subducting interface in your grading, like in your mesh setup or parameterization?
it's only first arrival. There is no floating horizon, so everything is constrained by first arrival tomography. We didn't invert it for reflection phases.
No, which means that when you do you do ray tracing at all? 3D ray tracing,
Yes.
like a Sapon Jaws group did. So it
Yeah,
is.
we ray trace like 4.2 million ray paths like at every iterations.
So when you do the ray tracing, is it a ray tracing from an initial like 3D model already, or what?
So we started, our starting model is the model from Nakanishi et al. 2018. Where is it? I think it's later on. So it's from this paper. So we used a combination. So Nakanishi et al., they combined every 2D model that were produced along the margin. They interpolated in between, and they produced that starting model of the margin. And then we use that as a starting model for our tomographic inversion. So this is a 2D transect. So those are 2D transect through this tomography model for the starting model along those two dashed black and white lines. And after, I don't remember, 56 or 60 iteration of travel time tomography, this is the final model we obtained.
Okay.
But it is a regularized inversion where we smooth like first and second order derivatives, but there is no floating horizon. So we don't have a MO or we don't have a plate interface that's part of the model.
Oh, I see. So you don't have a strong interface inside your model. Everything is smooth. It's a volumetric inversion, volumetric velocity inversion.
Yeah, everything is smooth, but because we have so many array paths, it is still like not that smooth. I mean, the regularization is working, but there are so many constraints at shallow depth and intermediate depth and greater depth that you still obtain like a great resolution.
Yeah, of
so
course.
In fact, like, yeah, from resolution test, you will obtain like resolution at like even 25 by 25 by 5 kilometer sinusoidal perturbation.
Right. But that is still like volumetric velocity variation, not the, you still cannot capture the interface, which can be improved in the future for sure, because that is also important.
Yes.
Yeah, and also because you're talking about full waveform inversion, which means it would be nice if you already have the interface implemented already in your initial model, right? If that, I don't know which package that are you going to use. However, for SpecFam, you can implement all these interfaces at the beginning already.
Exactly.
Yeah, it's going to be better starting model than you just purely use such, smoothed model to start with.
Exactly. Yeah. No, it could be used using SpecFam to even better constrain the resolution and the material properties of the margin, because there is still a lot of information that's hidden within the waveforms.
Yeah, it looks like you have 25 kilometers of resolution, right?
I mean, it depends where, but there is roughly like a triangular shape. So in this region, that tracks the plate interface. So all the best constrained region is roughly the plate interface.
Okay, I'm gonna jump in and cut it off because we're 1 minute from the panel starting now. But thank you again so much, and really great discussion. There are more questions still in the chat, so Adrian, if you wouldn't mind taking a look and answering them when you have a chance. I also want to remind everyone that we do have kind of a 15-minute window after the panel for additional general follow-up and discussion. So if you have still burning questions for the speakers, you can go ahead and ask them during that time. But now I'm going to turn it over to Lindsay to start off our panel.
Hi, everyone. Welcome back from the break. Thanks to Helen for moderating this morning, and to Adrian and Anne for those really, really nice talks. So we are in the middle of the Shoreline Crossing Science session. And now we have an hour and 15 minutes for our panel discussion and question and answer session on sort of how to build an amphibious experiment. So the objectives of the panel are to provide some perspectives and initiate discussion on lessons learned and major results from past experiments, and look forward to new opportunities as well as current and future instrumentation and facilities. I want to thank the panelists for their participation, and I think we have a really great group that represents a huge depth and breadth of experience to talk about things more from the science and the PI side and the experimental side. We have Jeff Abers, Susan Schwartz, and Ann Trehue. And not to make them feel old, but each of them have spent multiple decades of their careers really pioneering and thinking about and implementing amphibious studies. And then following that, we'll have Nathan Miller and John Collins and Pascal O'Day. They'll take us through some new instrumentation, innovations, and opportunities through different OBS facilities. So for the first part of this panel, the next kind of 30 minutes or so, each panelist will have a few minutes for introductory remarks, and then we'll open things up for discussion and Q&A from the audience for the last half hour or 45 minutes. So if you have a question, feel free to add it to the chat at any time, or you can raise your hand when we're done with the introductory remarks, and I'll work on moderating the discussion. So first up, we have Jeff Abers, who's a professor at Cornell University, and I think I'll let him share his screen.
Okay, thanks, Lindsay. Let's see, this is always the risky part of this. Whoops, all right, you all move it over there. So this is a panel, I guess, is my understanding is not about the science that's come out of these projects as much as sort of the nuts and bolts of how these are happen. And yeah, Lindsay called us old, so I think we can start with things we did a long time ago. I, like many of us, got our start working on land doing earthquake seismology. And so I thought this first slide is sort of how I got into doing this stuff offshore. My first truly amphibious project was in the Woodlark D'Entrecasteaux Rift of southeastern Papua New Guinea in 1999. We put out a short period array of a small number of OBSs and hydrophones and 11 sort of broadbands onshore. And the issue here, this is a place where oceanic rift is propagating into sort of continental-ish crust and see some of the fastest rates of extension on the planet. And so to understand this, we have islands and there's basins and there's rifts. And so it makes a lot of sense to put stations onshore and offshore. We did this once 20 years ago, went back 10 years ago in the CD Papua project, different collaborators, slightly different focus, but again, and a few more instruments, more broadband, modern instruments. In both of these cases, these are sort of classic PI-driven collaborations. These are part of a much bigger project. The second one, for instance, had an army of geologists and petrologists studying these green rocks onshore, but we as the PI team, so that one had me and Jim Garrity as the seismologists on the project, and Laura Wallace doing GPS. We could sort of plan and think about what exactly we wanted to do so it could mesh well with the other parts of the program. We also got to pick and choose some lovely little field vehicles like the Miss Rankin here, which we can talk about some other time. It's probably a good moment to I was thinking about what is important to structure here. People have made this distinction between community and non-community projects. And it's, some of it's a size thing, but it's not really, in the sense that, what I'm calling a PI-led experiment is one like the ones I just showed. PIs design them, have restricted use of the data for at least some period of time, and, someone gets first dibs. There's an in-between thing, and we're seeing more of these lately, what we call open data experiments, you might call, where, again, it's the experiment that the PI is designed that has to meet, do with their objectives, but all the data becomes open immediately. And then, but I think, the thing that we're sort of here to talk about a lot are these big community experiments that are large enough that funding agencies, feel like that level of resource needs a higher level of planning. These are community workshops that have planned and designed them. And again, all the data are open. And the two big ones in this world that I'm talking about are the Cascadia Initiative and the Alaska Amphibious Array. Hopefully someone else talks about some of the other ones. But these are two I've been involved with. Just and sort of step through my perspective. Okay, so on the Cascadia Initiative project, you probably all know about what happened here. I actually didn't go to sea. I was sort of working more on the planning phases, helping organize some of the early planning parts of this and oversight committees. This thing really came about very quickly when the 2009 Recovery Act was passed, and ARA funded the development of a fleet of seismometers, ocean bottom seismometers, as well as some on-land instrumentation. We are, pretty much out of the box. This was something that was going to be here in Cascadia. We made some quick planning workshops to work through the details and the phasing, and there's a 2010 workshop that called for PIs to do the marine part, and it set up this 4-year phasing plan at these different maps. And this is from a lovely article that Doug Toomey wrote in Oceanography summarizing what happened. This was a lot of work for a lot of people. I think there were on the order of at least 6 cruises, a deploy and recovery cruise for each instrument setters, OBSs, every year for 4 years, a bunch of other things going on land. There were, however, this is tremendously successful in bringing a lot of people in. There were workshops before, during, and after this. The data would become open, and I'll show you some stats on this later, but I think this really had a lot to do with the sort of opening up of this kind of data to a broad community. I guess the only thing that I would sort of say, because of the way this came about, the land part of the data acquisition was sort of set in stone before the OBS part was planned in many respects. So the coordination, I would say, could be better. Before that ended, it became pretty clear, though, that this was a very successful model. And so after Cascadia, there was, well, what next? And so we held a planning workshop, this in Snowbird in 2014, where we really looked more broadly at the problem, where you might do something like this. Out of that came sort of a fairly strong consensus that while EarthScope was in Alaska doing something offshore, continental Alaska was really important. The area that ruptured in 1964 and the places to the west of it were high priority targets. So we had a call for PIs, develop a proposal for this ACE, the Alaska Amphibious Community Seismic Experiment. And this gets talked about a lot at this meeting. You should, Grace Barczyk has a poster next week that'll sort of go through a lot more of the details of these data. This was after Cascadia. The thought was to extend the life of the instruments so that they'd be able to stay on the seafloor longer, do this all in one shot, and have a lot more sort of coordination between the onshore and offshore parts. It also served as a vehicle for, we added nodes. Lindsay coordinated another 400 dense array of nodes that we heard about last night. There was offshore air gun shot, temperature sensors, and so on. And again, not just open data, but we've been working now on generating seismicity catalog with that. And so I think this is sort of one of the 2 main points I wanted to make here is that this issue of releasing all the data as quickly as possible does a lot to democratize science. This is on the left a figure from Doug Toomey's Oceanography article, where he's showing over the course of the first 2 years of the data being available, this really rapid growth in just the number of unique users every month who tap into the IRIS data center and download the seismograms. That's still going on in ACE. To take this a step further, we've actually partnered with the USGS and the Alaska Earthquake Center to produce a catalog that's being released. The first half of it just came out last week through the same mechanism that all the other USGS hosted catalogs are being generated. So, these again are things to help democratize the science. And the last point I want to just make is, these things are a lot of work for a lot of people. I think there's a real issue of scale. When are these things big enough to be worth it? I think one issue we've seen is, we have the opportunity with a big program to bring in early career PIs to help, but it's a lot of work for them. And it's not always so clear what the reward, and that's something we're still grappling with. A lot of opportunities exist for education and outreach because of the size and the structure of these things. And Abria Adams will talk about some of that in a few days. The last lesson we learned from ACE, which was really the most annoying one, is, there were in a 3-year period, 3 magnitude 7.6 to 7.9 earthquakes in the footprint of this array. And in the 15 months of recording, we missed all of them. So I'll hand this over to somebody else.
Yeah, thank you very much, Jeff. And if people have questions for Jeff, you can hold them until we finish with the rest of the panel members. But thanks for that perspective. So next we'll have Susan Schwartz from University of California at Santa Cruz. She's on here somewhere. There she is.
Okay, I unmuted successfully, and now since I already shared my screen, I'm not sure I can show myself. I will as soon as it's over, the slides are over, okay? So can you see, does it look okay? Oh, start my video. Someone sent me a mess, there we go. Okay, and is it full screen for you or good enough, big enough?
It's big enough. We see the slides off to the side, but.
Oh, I can make it full screen. Let's see what happens. How about now? Hello?
Oh.
You
we still need the ones off to the side, but it's okay.
Oh, okay, never mind. Let me, sorry, I don't know what. Now I lost, okay, this is, I can't, all right, well, I'm not sure I can't control the stop sharing. Can someone, okay, hold on. Can someone, oh, there, all right. Can someone stop my share and I'll just leave it with the other way?
Let's see here.
Wait, maybe now. Somehow when I stop share, it just.
There we go.
Did you force my stop share?
I did.
Oh no. Damn it. I'm stuck. Maybe why don't we go on to, oh damn it. I can't, what do you see? I see a block screen. What do you see?
Okay. Well, we stopped sharing, so yeah, we could go on to Anne if you.
Or if you can control mine, because I lost my screen. But if you see me and you can.
Yours. Yeah, I have yours. So let me try this.
Okay.
So I can share my screen.
And I can. It's the double screen. All right. Okay. So yeah, go to back. That's the last slide.
Oh, sorry.
Go back to the first. Okay. While she's doing. Okay. So I was a PI on both the Cascadia Initiative and the Alaska Amphibious Community Experiment, but I also started doing shoreline crossing experiments way back, actually when Jeff was in the Western Pacific in 1999 to 2000, I was in the Eastern Pacific offshore of Costa Rica. And I was involved in an experiment, again, in the style of kind of individual or a group of individual PIs. And this was to look at the seismogenic zone off of Costa Rica. And the experiment consisted of about 20 land instruments. And at the time, those could be borrowed. The Pascal facility existed where you could go and borrow equipment. But if we wanted to understand the whole plate interface slip behavior from the trench, obviously, to the very the down dip edge of where it was generating earthquakes, a lot of that was covered by ocean, and we needed OBS. And at the time, there was no facility to borrow instruments. So when you wanted to do this, you either had to own the instruments yourself or collaborate with someone who had them. So I collaborated with Leroy Dorman, and we used his OBS instruments from Scripps, and we had 14 of them. And we collected some great data. It was very much worthwhile. We learned that the very shallow part of the plate interface did not have much, if any, seismicity. And at the time we thought it was locked. Since then, we learned that actually slow slip events occur there and take up the slip budget. You know, doing so, although it was kind of in the mode of individual PI, it was still it was funded by the Margins program. And I think being part of a program like that has consensus science made it possible to actually do some of this work. So even though we talk about individual PI, it's very expensive to do these kinds of experiments. And in general, being, you know, either addressing questions that are part of some kind of consensus, whether it's a community experiment itself or part of a bigger program, I think is quite important. Okay, next slide. So my next experience with shoreline crossing, Lindsay, can you, yeah, was the Cascadia Initiative. And Jeff, not 4, it was 14 cruises. So this experiment was a 4-year experiment, 14 cruises, about 280 OBS were deployed. So it was extremely complex. It really exhausted a lot of resources, both personnel resources, financial, but as Jeff mentioned, it was really, really important. It was important for growing, I think, the community of marine seismologists, for engaging early career folks to get involved. And the open data has been used by a huge number of people, and some really great science that has come out of it. So I was involved, and this is a next one, September 2012. I was chief scientist with, or co-chief scientist with Doug Toomey. And then again, if you advance to the next one, in 2013, another cruise with Jeff McGuire. So go to the next slide. So we, Jeff mentioned about land. There wasn't as much coordination with land instruments. We learned that basically in the kind of 3rd year of this experiment, that we had these great, really dense network of OBS instruments, but yet then we were actually sparser coverage on land. And so in the last year of the Cascadia Initiative, we realized we were doing this dense network over by the Mendocino Triple Junction, the OBS, or the blue triangles. We better densify and have at least the same kind of 10-kilometer spacing on land. And so Ann Trehue and Doug Toomey and I really pushed to get some land instruments to densify, which were the green triangles were the land component to match this. So that was something that was quite important. Okay, let's see, next slide. Oh, I wanted to mention just time, although it wasn't a community experiment, and talked a lot about hobbits. So I was on a Hobbits cruise and involved in that. And so I'll be happy when we get to the panel. I'm not going to talk about it now, but to answer questions also about the Hobbits experiment. Okay, and then let's see, the last couple slides have to do with the Alaska and amphibious Alaska community seismic experiment. And here I actually returned to my roots as a land seismologist and was involved in this experiment, was a PI, but involved in deploying and recovering the land instruments, which you'll see in the next slide. And I think, let's see what I wanted, comments that I wanted to make here. I mean, I think we certainly learned from the Cascadia Initiative that 4 years was much too long and too complex. So this was a 15-month deployment where we could get 2 summers. We didn't have to pick up and redeploy instruments. I think we're going to talk a lot more about the science that is being done. So I think really I'm going to just stop there, and hopefully my experience, I'll be able to answer questions that people have.
Okay, thanks so much, Susan. It's great to see those field pictures. Okay, so next we have Ann Trehue from Oregon State University.
Okay, I am sharing my screen and putting up my slides. Slideshow, play from start. Do you see my slides here?
Looks good.
Okay, great. Yeah, I don't have any pictures of myself in here, but this is my controlled source amphibious CV. Doesn't include the natural source experiments like Cascadia Initiative and a few others, but The first was in 1986, the GLIMPSE experiment, Great Lakes International Multidisciplinary Program for Crustal Evolution. And I think that may be the first experiment that recorded densely spaced airgun shots into OBSs and land stations. And it was a collaboration with USGS and the Canadian Geological Survey and 7 different universities in the US and Canada. Contract ship, and then followed very soon after by the Central California Margin PG&E Edge experiment. And again, a collaboration with some industry input, NSF, onshore instruments, offshore, and merging the two. I remember these because I was pregnant going out on GLIMPSE. I had a newborn baby during Central California. And then it's been followed over the years by a series of experiments in Cascadia, ever more ambitious. And we'll talk about the one coming up this summer, but starting in 1989 with funding from NSF MGNG and NSF EAR to piggyback on an ODP site survey and get out 8 OBSs from the University of Texas and 10 USGS 5-day recorders to record shots from a commercial airgun line. The Mendocino Triple Junction Seismic Experiment, Orwell, which was an international collaboration between USGS, GEOMAR, and Oregon State. Ships Experiment, again, a big collaboration with 250 RefTechs onshore recording offshore shots, no OBSs in that one. In 2012, Ridge to Trench, Coast, and onshore piggybacks. Jeff was involved with me in an onshore piggyback to the Ridge to Trench. And now the Cascadia 2021. And I do want to point out, and this was also a point made by Adrien, that the US data sets are cumulative. You know, so we're just building up better resolution. Prior experiments are much more limited, give you keys on where is most important and what kind of density of information you need. And then we've also had 2 recent experiments in Chile where the objective is to see how crustal structure influences slip and great earthquakes. So, you know, Cascadia is a little difficult because we have very fuzzy information about the great earthquakes there, but in Chile, the information is much clearer. And those were also collaborations, international collaborations with instruments onshore, offshore, on the seafloor and picture. And so that's basically my controlled source amphibious CV, but the slides are not advancing. There. I do want to remind us all that amphibious experiments are not new. In the 1960s, there were some very large experiments, very ambitious. This one on the East Coast, which was funded by ARPA, ONR, NSF, the Coast Guard, and USGS with 2,000 to 2,000 pound shots. Those are these spots offshore. 200 plus instrument seismometers onshore and buoys offshore, 12 institutions involved, and multiple objectives, both mission-oriented and basic science. There's a reference for that. There was also a similar scale experiment, possibly larger scale in the Gulf of Mexico with recordings onshore from Florida to Mexico. And the lesson here is that, you know, the more things change, the more they don't. It is still quite important to pull together a big group and to have multiple objectives and to have a balance between kind of applied and pure science to bring in the multiple groups to support these experiments. And another point I wanted to make, that there have been really step-like transformational increases in capability due to the development of technology. And the sources, you know, between the 1965 experiments when I was in grade school, and most of you were probably not born, the development of large airgun arrays, which enabled experiments of the sort we started doing in the 80s. Although no airgun array will compete with a 10-ton shot in terms of propagation. And then the receivers, there was a really transformative impact of having large numbers of portable instruments able to record digitally and continuously for a long time. And Susan made that point too, you know, pre-1990s, there was a trade-off. There were a few instruments with long recording time, recording on little cassettes, or many instruments with very short recording time. The SGRs that Stanford had that could record for basically a few minutes, but there were on the order of 100. And Pascal, the development of the Pascal instrument pool, and then later the OBS instrument pool, really increased the number of instruments one could field. We are, you know, this is ever growing N, and now the nodes are leading to another order of magnitude step. So, you know, the first Cascadia experiment, 89, 10 instruments on land, then we went to 100, and then this summer we're going to 1,000. And the planning and permitting also has really been affected by the development of Google Earth and other Earth surface mapping apps and the digital databases for roads and land ownership. And we've just discovered the hunting community is a great resource for getting names and phone numbers of people. However, it's as you go up 2 orders of magnitude, it's still a lot of work, maybe not 2 orders of magnitude more work, but a lot. And I would definitely don't choose to do this in the middle of a pandemic. And now for the Cascadia 2021, I'm sure Nathan will talk about the offshore component. This map here is showing the layout of part of the experiment. The light orange lines are the MCS lines planned, and there are lots of OBSs and bottom nodes on that, which Nathan, I'm sure, will mention. But these symbols onshore are the planned stations, and it's a combination of a broadly distributed grid and some dense lines. The PI team is myself, Emily Hooft at the University of Oregon, Kevin Ward in South Dakota School of Mines, and Aaron Worth at the USGS. So again, we have a combination of the more pure subduction zone science objectives with rather focused ground motion objectives that are bringing in USGS support. And the different symbols here are different ownership zones. We're first working on National Forests, Bureau of Land Management, Oregon Department of Forestry, timber companies, and private owners, and it kind of light up the map as new permits are obtained, when a lot are obtained at once, like the big white squares, which are, I think, Oregon Department of Forestry. We break out the champagne. And the plan for the experiment on shore is a seismic boot camp for 3 days in Corvallis in late May, followed by 10 to 15 teams fanning out throughout the region to get these instruments on the ground and then recover them a month later. And we just closed the call for volunteers, which yielded 232 applicants. And I think that is all I really wanted to go over right now. So I will stop sharing. I do have a few more slides that if they come up in discussion, I'll share again, but I'll stop sharing here and go on to the next one.
Thanks, Anne. Really good advice about not choosing to do these experiments during the pandemic. We'll try to
yeah, you know all about that, Lindsay, don't you?
All right, next we have Nathan Miller from the USGS.
Okay, I'm unmuted. Yeah, I just wanted to quickly show a map of the offshore section of the Cascadia experiment that Anne talked about. That we originally tried to pull off last summer and we're delayed till this summer, but it looks promising that we'll go this summer. So, so we're rotated here, right? So north is to the right, and Newport, Oregon here, Vancouver over here. We're going to shoot these blue lines as a project, or MCS lines, and a project led by Suzanne Carbat, Sheehan, Pablo Canales, and others offshore on Langseth. And then we're going to record those on ocean bottom seismometers from OPSIC, so 115 sites of those, and then a bunch of ocean bottom nodes that are contracted from an industry supplier, industry operator. So I thought I'd use this to motivate a couple of thoughts on what was said earlier and kind of on the experiment design side. And I think, you know, this project, this effort is an example of where a bunch of different individual PI driven style experiments have kind of come together. So there's the MCS group, which is an NSF proposal with kind of a hybrid open data access model. There's Ann's group, which is a PI driven with a lot of people and a lot of different hypotheses under that. And then there's our USGS interest in getting some ocean bottom data, which is also an NSF proposal. And so all those groups kind of came together. You put us all in a room, I think we have a community experiment. And certainly if you add this on to the rest of the work that's been done in Cascadia, you have just the latest stages of a big, long community experiment. So I don't know, that's one way to look at it. I think there's advantages to going this sort of route where you have individual PIs, you're focused on specific hypotheses, and importantly, you have groups that are vested in seeing an experiment through its hypothesis design, experiment design, and all the way through results. The downside, of course, is access and accessibility from a variety of people. And I think you get around that through data access, data release, of course. But importantly, I think data products, high quality data products, and accessibility of those products is key. It's certainly something we think about USGS, and examples there would be, we're interested in this project in particular to improve the velocity model. I think Adrien amazingly showed the value of 3D velocity models in subduction zone science. It's also hugely valuable in our hazard science. And so that's something we're thinking about. How do we improve those models? How do we get those out there to the community so they're best usable for things like rupture simulations, but also all the way down to, you know, paleoseismic observations. How do we interpret paleoseismic observations that people are making onshore and on the forearc with rupture models? How you link those things? A link is a high quality 3D velocity model. So in the same, you know, some similarities there are like with the ACE catalog coming out, you know, that takes a data set that in its raw form, sure, is released, but makes that data set much more accessible to a wider group of people. So I think we need to keep thinking about those things as we design these experiments and balance that with the interest of individual PIs and motivating and encouraging individual people to vest themselves in pulling off these experiments. So I'll leave that there and we can go on to the next one.
Thanks, Nathan. Next we have John Collins. So we're going to kind of switch focus a little bit into more instrumentation facilities. Thought that might be kind of a cool combination to talk about the science and the instrumentation in the same panel. So John Collins is at Woods Hole, and he's the director of the Ocean Bottom Seismometer Instrument Center.
Hi, I don't have any slides, so I'm here just to talk about the instrumentation end of things. And we've heard some great recaps of some older onshore offshore experiments, and obviously there are two very exciting onshore offshore experiments happening this year. But I would like to point out, you know, that the number of OBSs available to the US community is limited, right? And we have about 100 broadband OBSs, and strictly speaking, within OPSIC, there are only 28 short period OBSs. Now, obviously, we're not just deploying 28 short period OBSs for Cascadia and Queen Charlotte, where OPSIC is allowed to issue subawards to other institutions to use their OBSs. So when you do that right now, you know, when we subaward to Scripps, we end up with about 100 short period OBSs. So between the 100 broadbands and the 100 short period OBSs, you know, that instrumentation is aging, right? And one of the potential benefits of moving from OPSIP to OPSIC that NSF brought up from the very beginning was there might be some room and money for recapitalizing the OBS fleet. And I think that's going to be essential. I think going forward, we need that recapitalization to be able to field an adequate number of instruments with appropriate capability. So that is something I think that's a challenge for us as a community. Pascal is going to talk about the new Canadian OBS facility. Clearly, that is something that we should also be able to coordinate with and somehow use their instrumentation so we can get more instruments on the seafloor. So I'm here to answer any OBS questions that you may have. Thank you.
Thanks, John. And I think you probably just got off a boat, so thanks for being here for the panel. So next is Pascal O'Day. He's at the University of Ottawa, and he is, as John said, here to tell us about some exciting new developments with the Canadian OBS fleet. And you might be muted still.
Okay, I'm back. Sorry about that. Okay, now is all good? You're seeing my slide?
Yes, looks good.
Okay, so after listening to all the previous panelists, it made me feel like I'm kind of the new kid on the block here with some shiny new toys who want to make friends. And that's actually probably not that far from the truth. I personally don't have actual experience at sea, but I'm part of this group who's developing this, this national facility for seismic imaging to build a fleet of broadband OBS in Canada. So I'm here on behalf of this group, the NFSI, and in fact, this is the first time we officially announced this facility to the community. And I remember 4 years ago, the OBSIP meeting 2017, almost 4 years ago, Doug Weens was announcing that this project was funded. Well, it took 4 years to actually get it started. And this is in huge part thanks to Mladen Nedimovic, who's the project director. You probably will know Mladen more than know myself. Mladen is at Dalhousie University here. This is where the facility is hosted. And we have personnel Graham Cairns, who's a facility manager, and Katie Boston, marine data technologist. This was funded through Canada Foundation for Innovation through this 9 PIs plus Mladen, of course. So we're all spread across the country, representing most of the different provinces. Yes, we do line up on the south where it's warmer, but we have plenty of coastlines to explore. Canada actually has the longest coastline, I think, if you add up all of these islands in the north, but very few people live there. Anyways, I'm here to talk about the facility, and let's go right in. So don't have many slides. This is going to be pretty high level. It's just starting, and the project was born out of these aging OBSs that were designed at Dalhousie, and they were decommissioned in 2015. And therefore, we needed a new fleet of instruments. There were only 24 of these short period OBSs. And these are the instruments that we're getting. The Geralt Aquarius, these are broadband OBS stations. And we're gonna have 120 of them, plus one for spare parts and calibration in the lab. So these are some of the specs in terms of bandwidth. They are 120 seconds to 100 hertz. So this is good for earthquake monitoring and structural imaging using broadband techniques, a similar bandwidth than we have with land broadband stations, for example. 24-bit dynamic range, and hydrophone, 100 seconds, so very low frequency hydrophone, differential pressure essentially, with which you can do acoustic monitoring and compliance studies. And there's more sensors inside this station here. We went for low profile compact instruments as much as we could so that we could mobilize them quickly, stack them easily, and therefore we opted for this design here. This is almost exactly what we're going to get, but not exactly. We're going to have a different device here for recovery, for example, but they will all look like this. So with a compact instrument, there's obviously some limitations. So our battery package allows us to only deploy for 52 weeks. And also they're not trawl resistant and therefore not suitable for any deployment on the margin. Low deployment depths, essentially. And this is just a 10-second video of a factory test where you're seeing this tank where the OBS is at the bottom and the burn wire is here. You'll see this mechanism releasing the arms that hold the plate, the anchor at the bottom, just to show you what this will do underwater. Obviously, this is a control factory test, but nevertheless, I think there's even some sound, so I'll shut up for 10 seconds. So you see these are the arms that hold the thread that hold the anchor at the bottom together, and then the burn wire just burnt and released these arms. And there's not all about the facility. There's additional infrastructure at Dalhousie. There's an instrumentation lab and some offices, some office spaces. This is the instrumentation lab with some workspaces where we can work on the instruments and recharge batteries and things like that. A portable electronics lab for quick turnaround, a knuckle crane for deployments from smaller ships. And here's the timeline for this project, well, for this facility. So effective start date was essentially January 1st of this year, so it's brand new. First sea trials will happen this summer, probably around Dalhousie. And first full facility test, well, not full facility test, but facility test between summer 2022 to summer 2023. And so possibly around some experiment that is currently planned. This is yet to be determined. And we'll have the full facility with 120 broadband OBS by the end of winter 2023. And therefore first large-scale deployments possible around the summer of 2023. And finally, these are some of the targets that we proposed in our funding proposal, and they're obviously related to the waters around Canada, but this is going to be available for any international collaboration, of course. And we're very interested in what's going on in the Arctic. You see all of these earthquakes in northern Canada, as well as plate boundaries to the west, and some passive margins to the east with St. Lawrence River here, lots of earthquakes. And obviously international projects as well are very welcome. So if you want more information, we have a website, simply nfsi.ca, and email if you have questions about the facility, nfsi@nfsi.ca. And we invite you to sign up on our mailing list. You can find it on the NFSI website. We also have a GitHub organization page for some of the open source code that we're developing, and we have a SIG actually planned tomorrow for one of these. This is the OBS contract announcement by Graup and by Dalhousie, and we're open for business, so get in touch about opportunities and collaboration. So I'll stop sharing and hopefully have discussion about this.
All right, thank you, Pascal. Looks like a really exciting new facility. So we have about half an hour left in our time for the panel, so we can open up to questions from the audience. But first, I actually wanted to give the panelists an opportunity. If you guys have additional comments after hearing everyone speak, or if you have questions for each other, feel free. Okay, well, let's move on to some of the questions from the audience then. So Donna Shillington popped into the chat to ask about this kind of open data community experiment question that I think we all sort of grapple with sometimes. So she says, open data are great for increasing participation in marine seismology, but the 2-year moratoriums for the traditional kind of PI experiments provide some protection for people who are new to a method or a data type, such as graduate students. So what's your opinion? Should all data, both PI and community, be made open right away? And what do you think is the right balance? Looks like Susan is unmuted, so maybe.
All right, well, I mean, I think it does depend on scale. I mean, I think if it's a community experiment, and I think most of the community experiments, they're more senior personnel have volunteered because it is very, very time consuming. And as Jeff said, in general, it's maybe not the best investment for early career people to be on the planning and the actual being the chief scientists or the principal investigators. It's a lot of time, especially when the data are publicly available for everyone to use. But I think it's, we've had enough participation from people that I think that style experiment, it's really important and wonderful for the data to be available immediately. Smaller experiments, I think, having a moratorium makes sense. So I think maybe, and that's, with the land seismic, right? Pascal experiments that are PI have that same moratorium. And I think that's worked fairly well. So that's, my opinion.
Maybe I can leap in here as long as I've been thinking about this a lot, and because you do a lot of these things, and starting from an era where none of these things happen, you come up with actually, frankly, there's a little bit of discomfort in this. And I think it does, first revolve around your graduate students that you encourage to be part of these projects, and, them not having the kind of protections they have to sort of figure out how to write those first papers is a real thing. And I think, so I agree with Susan, a lot of it has to do with scale. We're not the only community that's dealing with this. Earthscope is I think an example of a large experiment that can only be done in a community way. It's big enough to professionalize most of the data collection, though. And I think that, in some ways protected a lot of people from that. With the OBS parts of these experiments, we do benefit from a lot of support from the Instrument Center, which for the land parts of this we don't have. So there is a crossover point here somewhere. I think the other element I would sort of throw in there is sort of the range of things that people would think of doing with some of these data sets. And again, it becomes an issue of size, something where you're doing the entire 1 to Fuca plate or the size of ACE. It's very easy to think of a lot more things that any small group of PIs would not be able to do. And so there is benefit. As you get to these more focused experiments, that it's less obvious how that would work. So, so those are just some of the things that are rattling around, but it's a good question.
Other comments?
Can I give some comments?
Yes, I had a quick follow up on that, but go ahead, Johan.
Okay, I agree that that's good for 2 to 3 year time period to protect for people who are new for the method data, like grad student, and also for the team conduct the cruise. But in my opinion, I think the problem is after the data release, a lot of people don't know where to download it and how to use them. And for example, I come from a Marine Institute in Taiwan, and I have been processing data on ship. So I know it takes time, but nowadays I applied a PhD in United States, and my professor is a geologist, and he want to see some document, but the primary result is people process on ship is the standard procedures, which doesn't enhance the image too well. So in this case, they need people in the marine science to be a bridge to help each other in different fields.
Yeah, can I just put a giant underline under that statement? I think, to use various examples on the MCS data side, 2-year moratorium is great, and I think it's a good thing. At the end of that, though, those data are most useful if they're on a data repository in a highly processed form that, as Jeff said, is a professionalized product. that geologists can download, interpret, etc. And I think the same applies to a lot of these other data sets, including velocity models from OBS data, etc.
Anne, go ahead, and then it looks like Emily Rowland has a question. Go ahead,
Yeah,
Anne.
I just want to add to that. It is the data also, in addition to the products, the data are very valuable from these big experiments, and there are lots of different things that can be done with them. I think a real moratorium, as opposed to a moratorium that can slide and sometimes data disappear for long periods of time, is very helpful to the people working. But another issue is that, you know, as somebody, I'm speaking with the perspective of someone who's coming from a mainly soft money situation where I can only work on things that are funded. I can only have students work on things that are funded. It's important for the funding agencies to provide support for working on the data from these large experiments, adequate support. And that hasn't, I think, always been the case.
Yeah, and I think that's one thing that differentiates like the IRIS, you know, Earthscope type model from a lot of what we've done in marine science. There hasn't been that data side support as much.
Yeah, I think having an Earthscope program to fund the science along with the Earthscope facility was very, very useful. And, you know, the Earthscope program was seed money for a lot of projects. A lot of the projects that were funded by the Earthscope program were co-funded by other groups, but it really provided the seed money to take advantage of the data set. Okay.
Great, thank you.
I guess,
oh, go ahead, Jeff.
I was just gonna say, right, and so, I think everyone knows this, right, but I mean, it does seem to be a little bit of a difference in sort of the history of how sort of the active source and the earthquake seismology data sets have been collected historically. Because, I mean, I think, you know, these earthquake data sets have been deposited in the IRIS DMC in a structure that's fairly easy to identify, that people know about for a long time. I mean, I think since sometime in the early 90s, pretty much every data set that's been collected, you know, people know how to get to and people know how to work with. And so I'm curious, like, so on the active source side, if that is evolved to the point where people feel comfortable with that as well, or not.
Well,
oh, go ahead, Anne.
I mean, the Pascal Instrument Center in their software development has been working on that, and there's that PH5 format, and I did some beta testing of it a couple of years ago. I haven't actually used it because I'm drowning in my own data, but it's tools that allow you to kind of pick and choose out of some of these very large controlled source experiments, as opposed to downloading a single humongous file that may have, you know, the data you want and the data you don't want, and you have to sort through it. But yeah, one thing that is very important is to require comprehensive metadata and cruise reports and things like that to go with the data to make it more useful for other people, because that's something that's been somewhat spotty in the past. But getting
excuse me, I'd like to ask a question regarding
hold on, do you we had Emily and Sean Wei were
okay.
had their hands up before. Do you mind holding on to yours?
No problem. I just couldn't figure out how to put my golden hand up.
So go ahead, Emily.
Yeah, thanks, Lindsay. Everybody, I actually think my question has sort of been touched on already, but I'll just ask it one more time before we maybe move on. But it's really related to, I think Beatrice just sort of mentioned this in the comments too, that I was going to sort of ask Jeff, who is not only engaged in all of these community experiments, has been through the years, but also I think is currently department chair. And there may even be other department chairs here in this group of 90 or so people. And I was just sort of wondering about, you know, Susan mentioned that, you know, maybe it should be senior scientists that are engaged in these community experiments, but there was a pretty big group of early career folks involved in the ACE experiment. And I think there are a ton of benefits of that too, in addition to it being a giant time sink and commitment, and, you know, that you're kind of learning how to do it by being involved in the group. You're making lots of networking connections, and you do have some control that way over the science that's being done, right? Like more control, I think. And so, how do you, like, maybe as a department chair, what is your advice for young scientists or for other department chairs out here who could be listening? How do you decide whether to participate or not?
So I've just finished this like several weeks of these one-on-one review meetings, and I was hoping I'd be done with that by now, but I mean, no, it's a good question. And, well, you know this and Lindsay knows, I mean, we were sort of, it was a bit conscious in sort of getting ACE off the ground to have, we probably had a bigger PI pool than was absolutely necessary to do the minimum experiment. But part of it was this, is that we could bring in some senior people and some early career people. And I guess, so I would just sort of turn this around a little bit to you and sort of ask, so how well has this worked? How has the trade-off for, between all this thankless work that doesn't necessarily lead to paper, and then, the recognition and figuring out how to do these things so you can sort of take off and do your own things. Has this been worth it? And it would be one question. And then would you actually ever do this again? This is for you or Lindsay, I guess. Just, that's a good chair trick, right?
Yeah, I mean, I can quickly say that I think time will tell. I'm not sure, but I think there have been a lot of undeniable benefits for me, at least, I think, in being a part of this. And there has been many of the PIs that have been funded off of follow-ups as kind of PI-driven, focused experiments. So that's maybe one thing that, I don't know if that's been mentioned yet in this discussion, that's a little bit more of a traditional benefit. Like, people are being funded in the ACES experiment to work up the data, at least some are. But this is something I'm constantly thinking about myself, because I really enjoy this part of science, but I also am always worried that I'm spending my time in ways that maybe some people don't think I should be. So, I mean, maybe others in this group have other feedback.
Yeah, I mean, for me, I would do it again because it was just really nice to see how super experienced, amazing scientists go about the proposing and the logistics. And so for me, it was a really awesome learning experience, and being able to be, a co-chief on one of the cruises was really great. And I learned a ton. So, I would do it again. I think the learning opportunity was worth it. It was a lot of time and effort, but, so maybe in the future, we think a little bit more about how we can support some more science for junior people or students, but, I would do it again.
Let me, one more quick comment and I'll shut up here.
And then we'll go on to another question.
Yeah. I was stalling for time listening to you guys. But, this issue isn't really unique to seismology or marine geophysics or whatever. It's more and more, I think, data collection is this big collective enterprise. We see it in a lot of the NASA mission related people who, those big satellites take a lot of work. Armies of people involved in climate models that, papers have hundreds of authors on. And so I think this is sort of the traditional way is, in a way, stands out a little bit more as being different than this way. If you sort of look across departments and colleges and universities in terms of sort of what modern scientists really do. So it may not be as anomalous as you think to be able to point to involvement in these big community things as part of sort of a bigger package.
All right, thanks all. So let's go on to some more questions from the audience. So Sean Wei has had his hand up for a while.
Okay, wait, thank you. I just also want to follow the kind of conversation about the trade-off between community-driven projects, big projects versus PI-driven. I guess in an ideal world, we want to have these big projects, Earthscope, Cascadia initiatives, and then really recruit more people, attract more talented people into our community, and also try to build up our reputation even to the general public, and then even to make this pie bigger. And then on the other hand, we can also get more funding that's to fund more PI-driven projects. That's the ideal world. But on the other hand, also kind of heard mixed message about how like Cascadia or amphibious array Alaska kind of drained all funding resources and also instrumentations. And so I guess in general sense that this pie is getting bigger, but is that bigger? Is fast enough to, or is there any other ways we can really stand out to, of course, try to get money from other resources and make this pie bigger? That's my curious. Is there any such a trend?
Yeah, I think that's a good point. Go ahead, Anne. Yeah.
I would just say that's where, you know, having multiple objectives that range from the more pure science to applied can contribute. I mean, that does not apply to every problem, but if it is relevant to your problem, it is you know, it's what was done in 1965, the balance between understanding continental margins and knowing crustal structure for nuclear test detection. And it applies to the Cascadia 2021 in that, you know, we're balancing sort of the broader subduction zone science with the more mission-oriented science of USGS to improve hazard analysis. So, you know, that is traditionally been a way to broaden the pie for certain problems, for problems where it is appropriate. So you know, you don't want to exaggerate the applied aspects, but you know, when you also want to take advantage of them.
Hey, Lindsay, can I comment directly on Sean's question? I think
sure, go ahead, and then
I think he makes a really good point, and I think it's a key distinction, certainly for the offshore part, the broadband offshore community in particular, from a lot of the successful previous community experiments, really large experiments, in particular onshore, but even including Cascadia, that there was special instrumentation developed to support those programs. Earthscope did not utilize the Pascal pool, including for the flex array work. Cascadia was an entire new build of instrumentation that did not draw from the sort of the existing OPSIP fleet at that time. And so it still allowed for the space for PI experiments to happen. As John Collins pointed out, our OBS facility is really limited right now. And so as we continue to talk about and think about large community experiments, subduction zone 4D, SE4D being a really obvious one, I think we need to be really careful not to forget that PI-driven science is still a really core part of what our community wants to be able to do. And community experiments, even as successful as ACE was, put a big strain on those resources that really forced PIs who were putting proposals into the pipeline to sit and wait for those instruments to become available. And that's a trade-off that we need to recognize and think about carefully, I think.
Thanks, Jim. So let's go to, it looks like Pat had his hand up for a while, and then we'll go to Spar, and then there's some questions from the chat.
Thanks, Lindsay. My arm's getting tired. My question is regarding the large community experiments and the obligations to make the data publicly available. When there's an MCS component, like a Langseth MCS is part of one of these amphibious experiments. And so I'm not sure then, is there a requirement to make the field data publicly available right away, or is there a time to do the data processing and then the process data needs to be made publicly available as soon as it's done, whenever that is? Or back to the original question, are the field files to be made publicly available as soon as the leg ends?
Hi, Lindsay. I can comment on Pat's
oh yeah, on the Cascadia
question for Cascadia, yeah, which is the Cascadia experiment that Nathan presented. It falls in between these community experiments or PI-driven. It's an open access experiment. And in this case, yes, the MCS data, the field data is going to be available to the community right after the cruise and once it puts in a repository. And the process data, the product, that's going to be processed commercially. And I think that's a key thing that to fight for in the future whenever we do these open access experiments involving MCS is that we should aim to request enough fundings to get this data processed commercially. If we're going to make them available to the whole community and useful, that should be the standard. But there is a downside on that. We lose the training component for the students. So there's going to have to be a balance of keeping also other PI-driven experiments that are helpful for the training students in MCS processing and data analysis.
Thanks, Pablo. And I think that kind of relates to Juan's question in the chat where, you know, some of the release data is not necessarily usable by people who are outside the field. And that, I found that to be true with the MCS release. You know, there hasn't been a big tradition of releasing actual process, migrated sections. And so maybe that would be something that comes to the fore in the future, like you guys are doing with some of the Cascadia stuff. Right, Spar, I think, was next.
I just wanted to make this sort of obvious point when we've talked about whether early career and mid-career people should be involved in these big experiments in their planning and operation. The simple point is that people get old and retire, and it's important to have people ready to take over running these complicated projects. Awful lot of people running OBS facilities are getting close to the end of things, and we have a lot of old seismologists on this page, so I encourage the young people to step up. One of the things that's going on now is this setting up the new GPSA facility at Scripps. Dave Chatterall is retired, and so we need new people to come in and take over managing or at least directing those facilities as scientists.
Yeah, thanks, Spar. Looks like, Jim, do you still have a comment that you want to make? I think your hand was up before Colton.
I do.
Okay.
Thanks, Lindy. Yeah, so I wanted to kind of put out there, it's a question that I don't personally have an answer to, but I mean, this is an amphibious session, and I'm curious whether there is any sort of consensus is developing on whether we are happy with the level of technology that's available to us to deploy broadband instruments in relatively shallow water. And those two issues there that we deal with are both protecting instrumentation for long time periods from fishing and other activities, and the second really big issue is data quality and whether those data are actually useful once we do succeed in collecting them. And as many of you, I think, know, there was an effort about a decade ago to kind of build into the Cascadia instrumentation a couple of different ideas for how to try to deal with that I would argue were successful in many ways and maybe not so successful in others. And I don't think, to my knowledge, there's been much of a conversation about it since then. And so I'm curious whether this is something that the community needs to be a little more focused on if we are going to continue to improve the facility to do the kind of science we want to do, crossing the shoreline, where clearly shallow water environments are going to be important.
So Jim, I would just say that your question relates to passive monitoring, right? Traditionally, we have no problem deploying short period OBSs in shallow water and getting good quality data for active source experiments.
Yes, I agree. It's for the longer term deployments that for earthquake problems, for broadband seismology imaging, the kinds of things that we deploy for longer time periods for.
And the question there is unshielded versus shielded versus burial.
Yeah, I would say that those are the ideas that have been out there for a long time, and I'm not sure that we've come to much agreement on sort of the best way to do it, given the significant trade-offs in costs and other issues. I guess I wasn't necessarily looking for an answer or even to necessarily start a big conversation, but I wanted to put it in this group's, you know, kind of put it up as something that I feel like maybe our community could be and should be thinking about and talking about again.
It certainly is important as we consider recapitalizing the OBS fleet.
So it's a quick related thought question. I mean, there's been tremendous growth in the last couple of years about fiber optic interrogators and those sort of, systems that are pulling off very wideband signals from them. It seems like for these near shore environments, there's some other possibilities those things might open up, and it's a big different kind of investment, but I'm wondering if that isn't also something that should be on the radar.
It looks like Spar might have a response, and then we'll go on to Colton's question after this.
Yeah, certainly one of the interesting things that's happening that's relevant to the near shore is that this push towards smart cables, where you put in sensors into underwater communications cables, has really taken off. Alcatel is talking about putting systems out right now, several places around the world. Of course, the advantage of a buried cable is it doesn't get taken by fishing. It's well coupled. You have continuous data for long periods of time. That really, it's one of these things that we really ought to think about. You're talking about $100 million or something like that, but you'd end up with a place like off Cascadia where you'd be doing seismic hazard plus incredible data for long periods of time. I guess my other comment would be, having put an enormous amount of effort into building these giant trawl shielded instruments, the question is whether we actually need them or not. The amount of trawling that you get further offshore tends to be pretty minor. I'm not absolutely convinced that more than one instrument has ever been hit by fishing, either in Alaska or in Cascadia. Maybe we just risk it. It seems like the big shields do reduce noise at long period in shallow water, but they probably raise the noise level at short period. And so I think there's quite a bit of work that somebody else should do fairly soon on this problem.
Yeah, Spar, I would say you're optimistic about when you talk about trawlers hitting OBSs. Certainly a bunch of Hui OBSs have been dragged up by trawlers and returned to us, so we know how they were hit. And just one other comment: since OBSIC started in 2018, we have not had a request for the Lamont TRMs.
We lost a whole bunch of instruments around Sicily. That's true.
Yep.
All right. Thanks all. Colton, if you have a question, been waiting for a while.
So I wanted to make a point and then maybe move this discussion in another direction. There's been a lot of comment about how the short periods haven't been necessarily providing data in easy processing, in easy to process manner. The broadbands are not blameless in this either. The OBSs are not tilt corrected. They're not corrected in any way. And frequently they don't have they all don't have orientation information. So anyone who's not familiar with OBS data won't be able to just run it through their codes. So this is, not just a short period end member. One thing I wanted to bring up and get the group's opinion on is how we see sort of this new Canadian facility integrating with OBSIC, integrating with NSF. How easy will it be to use US flagged vessels to carry and deploy Canadian? Can you do sort of a joint short period, long period OBS deployment with a mixture of the different facilities? How do people see that actually moving forward, and what mechanisms might make that more useful rather than having our stuff and their stuff?
I don't think there's going to be any problem from a US perspective in collaborating with the Canadian facility, right? I think there are issues, but they're not at all insurmountable about using a foreign vessel, right? In terms of UNOL safety standards, etc. I don't think those would necessarily apply to, you know, working off a Canadian research vessel. Lindsay is planning to do it later this year. But I would like to go back to your one other point about orientations, etc., etc. Is Andrew Barkley is a recent hire in OPSIC, and he is tasked with producing data products for all OBS experiments, and he is just about to upload orientations for the ACE experiment to the DMC, and he will be doing that going forward for all experiments, broadband experiments, and will also be uploading compliance corrections. So it is something that he is tasked with doing. That's his #1 job.
Thanks, John. Pascal, do you want to comment on the Canadian?
Yeah, actually, I'd like to comment on those same 2 points. I think as John outlined, there is no real problem integrating those facilities, and the Queen Charlotte Fault project was doing just that when it got delayed by COVID, and we also were late with our delivery of OBS, but it was planned that way from the start. Canada doesn't have a dedicated research vessel, so that's one of the problems that we're facing. So we very much like to collaborate with the international groups. So I don't see any problem with integrating both 2 facilities together. And the other point regarding the orientation and compliance for the broadband OBS, those are both sort of estimated. They're not really, we don't know them 100%. So there is value in providing these kinds of numbers to the community, but they should, in my opinion, you should also stick with the raw data and try to kind of understand what this comes from and maybe do it yourself. So that's the reason we're trying to develop these software to orient the sensors and remove compliance, and Helen is leading this special interest group tomorrow to go over that. So there is value in giving this to the community, but with the caveat that these are kind of estimated numbers, and you should probably be careful for different, different processing you want to do with those.
Thanks, Pascal. Looks like Helen might have a comment on that.
Yeah, thanks. I just wanted to jump in really quickly on that. I agree with what Pascal just said, but I do think it is an important point to remember, especially in this shoreline crossing session, where there is probably more potential to have people that are primarily land seismologists working with this data perhaps for the first time. And if people are not familiar with kind of the suite of intricacies that come with working with some of this OBS data, and they just plug that data into whatever typical routine that they use for land-based analyses, things can not go well, sometimes even leading to erroneous results. And so I do think it is important for us to think about either how we communicate the proper use of this data, or at least providing, you know, some level of basic sort of process data that will be usable for most techniques, with the caveat that, you know, there may be intricacies that it would be better for the user to look into in more detail on their own. And so I think particularly in this shoreline crossing session, it's a really good place to talk about those types of data products, because it does have potentially a more outsized effect on the community of users.
I think it would also be good, the way the short period instruments are typically located is via shots from the the shooting vessel, and that usually happens much later after the data have been submitted to the DMC. It would be, again, people have brought this up again and again in the past, some mechanism for the PI to give us the orientations of the short period OBSs and their locations, so we could add those to the metadata at the DMC.
Thanks, John. I just want to do a quick time check. I see your hand, Emily. I just want to do a quick time check. So we're kind of, according to our agenda, we're sort of officially past the panel time, which ended at 12:30. So I really want to offer a huge thank you to the panel for initiating these great discussions. But we do have another 10 minutes until our break, so we can keep discussing. If y'all don't mind staying on, that would be great. So we'll go to Emily Brodsky. I saw her hand up.
Okay, sorry to go into the break here, but I wanted to query the instrumentation issue again. That was brought up, whether or not everybody's happy with the instrumentation. And in particular, it seemed to me like the long-term deployment question is a real question, and it seemed like that was a major design criteria of the Canadian facility based on what Pascal just said. And so, is that a solved problem now? In particular, as I understood it, based on your presentation, Pascal, you have to wait 52 weeks for that data if that's the mode you're going to go in. There's no intermediate data retrieval, or did I miss a capability there? And of course, that's a terribly scary thing to do, and it's outside a grad student's lifespan, hopefully. And are there other issues with the long-term deployment capability that we should be aware of? What do people have to say about this? And I guess I want to hear from Pascal, and I'd love to hear from anyone else as well.
Yeah, well, the answer to this is yes, you have to wait 52 weeks to get the data. There is, to communicate with the sensor, you essentially communicate to bring it up at the end of the experiment. There is no data transfer. And I think this is what has been happening in most of the broadband OBS stations, and people might know more about this than I do. Maybe there's new technology to go about this, like gliders or things like that, that the seafloor GPS is trying to do. But I don't know if you could do high rate data transfer on these platforms. But this is maybe a question to someone else.
You can do high rate data transfer using optical modem, which is what Hui has done. We put one on an AUV and fly the AUV to the OBS, but it's a very expensive proposition and is really not suitable at this point in time for a fleet, for an array of 50 OBSs.
It looks like John Orcott might have a response to that. Oh, it looks like you're still muted, John.
Yes, we have, as I think most people know, we have operated in OBS for several months, broadband OBS with a glider in place. And that has been able continuously to bring back 1 Hertz data on 4 channels while that is operating by way of Iridium and the glider that's overhead. The other advantage of this is that the time is well known on the glider, and over a long period of time it's possible to remove the drift in the time to about a 1/10 of a second per year using this technology. So, but it does involving another complex system on the surface that is not inexpensive. These gliders cost about $250,000 a piece. And but they do deliver a couple of things that are really critical. That is, it delivers the time, and it also regulates the clock over that period of time. And those are 2 major instrumentation problems that have a solution, albeit somewhat expensive. But I do have a poster later in the week, or next week, I guess, on this issue. Thanks.
Thanks, John. So I want to go back to, I see Sean Wei's hand up, but I want to go back to Emily had a question in the chat a little while ago, and Jim answered it, but I want to kind of bring it to everyone's attention. Emily, go ahead.
Well, yeah, I was just kind of asking, based on John's comment, what we, those of us interested in using this short period OBS fleet, what we can do to help recapitalize that sort of set of available instruments, if there are things we can do to help, whether it's discussions or proposal writing.
Yeah, I think community demand is the key to persuading NSF to recapitalize the fleet and to build a new short period fleet. You know, there is a proposal in right now under the mid-scale infrastructure. It's a pre-proposal to build 100 broadbands and 100 short periods node-like instruments. I suppose the chances are that proposal is not going to fly because it's, you know, it's a competition, an NSF-wide competition. But ultimately, I think NSF OCE needs to be persuaded that this is something they should invest in. And that persuasion has to come from the community.
Thanks, John. And I just wanted to point out before we go to Shanwei that Jim put a link to, there's a, you know, we have community oversight and guidance with the Instrument Center. So there's a UNOLS subcommittee that also has written a recent white paper. And I wonder if the white paper is available publicly at this point, Jim? Oh, there it is. Okay, so Jim put a link in the chat if folks are interested in that. All right, Shanwei, do you have a question?
Oh, I just have a very short comment on the about on the conversations earlier about the data processing. Well, of course, it's indeed difficult. It's more challenging to process OBS data. But however, I want to send a message to all the newcomers here. It's not that difficult. Don't be scared off. Like if you do P-wave tomography, you don't need to do orientation. You don't need to do the tilt correction. And even for surface wave tomography, tilt correction can improve a lot, but still, it's not that much work. You will spend a little bit more effort, but the value here, the benefits from OBS data is way higher than the burdens you will get. It's my comment.
Yes, thank you. Good point. See, I see another question in the chat about cabled networks, which we kind of touched on a little bit, but I don't know if anybody has additional comments on that.
I have a related comment, sort of, that, you know, we're talking about wildly different scales of facilities here, from cabled networks, real-time data delivery, through smaller scale things. And I think there's, you know, different places to place those. Something like, you know, the Japan model provides a nice example. You have a real-time cabled network that's a national level facility. It's a dedicated effort, more analogous to EarthScope. You know, and I think that's the place to put that. And then there's these other things that are, you know, instruments designed for individual experiments and smaller scale things that maybe fit under individual proposals better. So if we, you know, want real-time data delivery and a long-term monitoring effort, that's a massive effort, and I think needs to be supported as a national level facility.
Thanks for your comment. So we have 2 minutes left. So if we have any kind of closing comments from the panel, I would welcome those. And then we'll go into a break and we'll come back at 3 o'clock Eastern. Okay, I see a lot of red microphones. So I really thank you so much to the panelists for preparing comments and for initiating this discussion. It's been really interesting, and thanks to everyone for participating in the question and answer. So now we will take a break until 3 o'clock Eastern, and we'll come back with talks by Colton Liner and Jim Garrity to finish out the session. Thanks everybody, we'll see you in a few.
Hope you all had a good break. And now we're going to come back to end our session with 2 additional science talks, first of which will be by Colton Liner, who's an assistant professor at University of Delaware. And the title of his talk is Offshore Anisotropic Constraints from ENAM, CSC, and ACES OBS instruments. Take it away.
Ready. Thank you. Everyone can see the full screen? Perfect. So this was a very generic title, and I felt it was better than, you know, here's some anisotropy stuff I've done. But I'm going to try to cover two different community seismic experiments that span both ends of the geoprism spectrum. So I'm going to talk about the Alaska Amphibious Community Seismic Experiment. So that's part of the Subduction Zone Initiative, and the ENAM, Eastern North American Margin Community Seismic Experiment, which talks about you know, rifted margins. And both of these are amphibious in nature. So they're margin crossing, and I'll hopefully show in both of these that how important that actually is in our overall understanding. And some of this is, you know, just the lowest hanging fruit we can think of because we've never had instruments here. So that's what I'm going to touch on. So I'll start first with the amphibious community site, the Alaska Amphibious Community Seismic Experiment. We're going to see a lot of this, I assume, over the course of this symposium. We've already seen a little bit of an introduction to this, so I won't go into too much detail here, but this is a community seismic experiment. All the data is publicly available if anybody's looking for it. It included 75 broadband OBSs, so nearly the entire OBS fleet, and additionally 20 on-land stations. So this is the amphibious component of this. And most importantly, this crossed the plate boundary. So we have a lot of stations here in this map. Out on the Pacific plate, each one of these circles is a station location. We cross from the Pacific onto the sort of Alaskan peninsula, and so we have this entire suite of data that spans both sides of this convergent margin. And one thing I'll point out here, as we'll talk about this later, and we heard a little bit of it mentioned yesterday in Donna's talk, is part of this experiment spans the so-called Shumagan Gap in the Samiti segment. So this is an interesting boundary along the Alaskan margin, where we have these areas of, you know, recent great, so very large megathrust earthquakes. So that's what these orange dashed lines are showing, you know, generalized rupture patches of some recent large earthquakes. And then we have this Shumagan Gap, where we have this lack of large earthquakes in the past 150 years, while in the immediately adjacent Samiti segment, we have some rupture every 50 to 75 years. And one of the questions related to this is, why is there a gap? Is this incredibly locked and primed for a very large earthquake? Is this tied to some other type of slip along the plate boundary? Are there properties that make this so? And so there's been a lot of work looking at this, and I will touch on this here now with anisotropy. So we're going to approach this using a technique called shear wave splitting. Most of you have seen this before, hopefully, and you've probably seen this exact same figure because everybody likes a little animated wiggle. Shear wave splitting just gives us context on the seismic anisotropy of whatever the waves are going through. So in this case, it's going to be the upper mantle across that convergent margin. Most people have seen this in the context of mantle dynamics, olivine deformation. We often talk about, you know, flow in subduction zones, but shear wave splitting is sensitive to any source of anisotropy. And as we'll see here, it's not going to be just olivine, it's going to be structures and, you know, mineral phases we can see in the subducting plate and the upper plate that also drastically impact shear wave splitting. So it's not just olivine, it's, you know, anything that gives us anisotropy. So I'll give a brief little primer here on some of the OBS characteristics that I saw at this, since, you know, the Alaska, the AACSE is relatively new. So as we just heard, and I didn't know that, and this is great, you know, I have calculated orientations for all of the stations, but it sounds like that's going to be business as usual, which is going to be fantastic and make a lot of this data set more usable. For this, I used Orient Pi, that from a nice set of codes from Pascal, and I don't know, but I think this might be covered in the SIG tomorrow, part of the OBS processing. This is a really nice set of codes that allows you to calculate station orientations using both P-wave and Rayleigh wave polarizations. And so what I plotted here are just station orientations calculated from the surface wave and from the P wave, and most of them fall on the one-to-one line. There are some interesting patterns to see in here if people want to discuss the AACSE OBSs more in detail. I would be happy to do that later, but we have orientations from the Rayleigh waves, and then we check them with our XKS polarizations. So we'll just jump right in to some of the shear wave splitting measurements. So what I'm plotting here are station average shear wave splitting measurements at each station. So the orientation of the black bars at each location give us the direction of anisotropy, and then the color of the different symbols gives us an average delay time. So we can think of average delay time as a proxy for strength of anisotropy or layer thickness, and then the orientation of the black bars, this is that direction of anisotropy that we're going to be largely interpreting. So this can be broken down into three main regions. So the offshore and the Pacific, we have all of these stations out here. These are trench parallel in nature broadly. And so these are true for all of these sort of further offshore stations. We see a similar pattern when we look further back in the mantle wedge. So the stations back here on the actual Alaskan Peninsula, these are sitting over, several tens of kilometers of mantle wedge material. And these also, again, have some variance to them, but are largely trench parallel in nature. Where we see the strongest or starkest pattern or change in anisotropy is in this sort of central region between those that are far offshore and those that sample a lot of wedge. So stations that are sitting just on the North American plate, that are on the upper plate, but are still largely just sampling the contact between the Pacific and North American plate, are not yet sampling mantle wedge material. We see a change in anisotropy from things that are roughly plate motion aligned. So if you look at stations here on the eastern side, so we have all of these orientations are aligned roughly with the convergence direction from the Pacific plate beneath the North American plate, and then they transition nicely into sort of highly oblique to more trench parallel orientations over here on the west near the Shumagan Gap. And this correlation with this change in anisotropy very nicely correlates with that boundary between things that rupture regularly in sort of these large megathrust earthquakes and this Shumagan Gap. We have stations are plate motion aligned, where we have these large megathrust earthquakes, and then in the Shumagan Gap we see this nice rotation to trench parallel anisotropy. So this gives us some notion that something has to be going on here, right? These stations are shallow relative to the mantle wedge. Sorry, I think in mantle terms, not yet OBS shallow depth terms. So these are sitting above, these are on the upper plate, but are not yet sampling mantle wedge material. So this is really only sensitive to a small amount of the upper plate and the downgoing slab. There's not a mantle wedge contribution yet in this, and yet we still see this really sharp contrast. So something has to be going on, triggering this change in anisotropic orientations from plate motion aligned to trench parallel. This is perhaps easier to see just sort of in simple graph form. All of these fast directions that are non-trench parallel. So this blue bar represents roughly the orientation of the strike of the trench. And it's a wide range because we have a curvature here. But most of the stations sort of offshore and then deep in the wedge here is signified by this big red box. They're roughly trench parallel in orientation. So I will note on this plot, the left-hand side, this is distance from the trench. So this is the Pacific plate. And then on the right-hand side, this is depth to slab surface. So this is using slab 2 as a model. So giving us a sense of where the mantle wedge likely begins. And most of these shear wave splitting measurements that have that trench normal or plate motion convergence aligned orientations are in this very shallow part. So they're not yet sampling large amounts of wedge material. So this isn't likely something that's a dynamics change. This isn't likely an olivine change. This is something that's actually going on very, very near the contact between the upper plate and the downgoing plate. So if we color in our rupture patches, it can sometimes be a little easier to see. I've also plotted this now against magnetic anomalies on the seafloor moving in, and this is not a new observation. Other people have argued many times that one reason for this Shumagan Gap and the Samiti segment are rotation in these incoming fabrics of the downgoing Pacific plate, and we see this helps illustrate that point. So we have these highly I keep saying highly oblique. I guess highly oblique can mean either orientation. So we have in the Samiti segment and further east, we have these fabrics on the downgoing Pacific plate that are more trench normal, so highly aligned relative to the orientation of the subduction zone. And then as we get towards the west, we have this rotation in tectonic fabrics that are more trench parallel aligned. And this correlates nicely with this sort of Shumagen gap and Samiti segment, this change in earthquake behavior along strike. And so this tectonic fabric has been linked before using other seismic techniques to changes in hydration along the margin. So this is some work by Donna Shillington and others, looking at two active source lines. So here on the left, this is an active source line near the Shumagen gap. On the right, this is for the Samiti segment. And we see some very stark changes as we go from one region to the other. So in terms of bathymetry, we see a much rougher bathymetry beneath the Shumagen gap. And when we look at the actual two-way travel times, you can see there's lots of evidence for bend faulting. Whereas beneath the Samiti segment, we see a much smoother varying topography, and we don't see sort of this bend faulting. And this has been suggested, as we've already seen today, and some people brought up yesterday, outer rise faulting can give us nice pathways for hydration to actually get down into the crust and the mantle. And this is something that is suggested through the seismic velocities along these same profiles, where we have the Shumagen gap and we have all of this increased bending faulting. We have this sort of reduced upper mantle velocities. And this is, as we saw earlier, potentially indicative of hydration in this upper plate. Whereas we don't see this enhanced bend faulting, we don't see these lower seismic velocities and don't have that strong evidence for hydration. And has been argued that it's that tectonic fabric that allows for increased bend faulting in the Shumagen gap versus in the Samiti segment when you have those tectonic fabrics aligned closer to the orientation of the trench. The bend stresses right in the outer rise can give way to increased faulting and then lead to hydration. And this is very important for anisotropy because hydration state can lead to very strong changes in seismic anisotropy in sort of the shallow upper plate. So this has been argued before in Costa Rica and in other regions where we have hydration of the downgoing slab can lead to serpentinization. So serpentine minerals are very highly anisotropic, much more so than, say, olivine. And when we add water to the downgoing plate, we can get this mineral phase transition and give us a new source of anisotropy for our shear waves to encounter where we have a lot of hydration. We can also get a shape preferred component of this. Normal faulting at outer rise is likely to be aligned relative to the trench. And if we have preferential hydration along those fault pathways, the contrasting properties of the serpentinized faults and the non-serpentinized material near it can also give us shape preferred anisotropy, all of it acting to produce trench parallel fast splitting directions. And so this anisotropy persists when we have this strong hydration. We need it to create the serpentine minerals. And then this is going to be lost as soon as we subduct further and we dehydrate the incoming slab. So this is not a permanent source of anisotropy. It's really only as long as we have persistent hydration of the downgoing slab. So you always have to have your own cartoon. So it's similar, but new exclamation point for what I think is going on here, how we can explain those shear wave splitting observations. We can explain them with a change in hydration between the Shumagen gap and the Samiti segment. So where we have increased outer rise faulting, where we have potential for increased hydration, we are going to get the strong serpentinization of the downgoing slab, which gives rise to this trench parallel anisotropy that we see in the Shumagen gap. In the immediately adjacent Samiti segment, where we don't have this preferential tectonic fabric that allows for enhanced outer rise faulting, we're not going to get sufficient hydration to really overwhelm any signal, to overwhelm what's happening beneath it, and we're going to get sort of normal convergent parallel anisotropy. We're going to get this plate motion alignment because we're not seeing enough hydration to allow for that serpentine signal to overpower everything else. And then as we subduct further and we get back into the mantle wedge, we're going to dehydrate the slab, and eventually we lose all of that hydration signal, and we get the persistent dynamics from the wedge throughout the entire region. And all of this tracks back to that preferential alignment of the tectonic fabrics. This is dependent upon hydration, but I think we have very strong evidence for that with these shear wave splitting observations. Now, this is the sort of hand wavy part of this, and you can't talk about subduction zone without a brief addition of earthquake behavior. This slab hydration and serpentinization can lead to a weaker interface and might allow for increased slip along the boundary that is preventing the Shumigan gap from really accruing enough stress to get to these magnitude 8 sized earthquakes. All right, switch gears a little bit. Now I gotta switch to the other side of the country, and we're gonna talk about the Eastern North American margin here briefly. So this is another community seismic experiment, again amphibious, onshore, offshore, shown here offshore of North Carolina. I'm going to talk about the 30 broadband OBSs, as well as sort of the TA, the transportable array, looking at anisotropy across this margin. So we'd previously done some shear wave splitting here, saw something very unusual. We see this strong margin parallel shear wave splitting at all the offshore stations, and then a stark transition to nearly null or highly complex anisotropy immediately onshore. Like most shear wave splitting, we then make a very pretty cartoon that says this is mantle dynamics and flow is complicated, and boom, now we know what the mantle is doing. But shear wave splitting alone doesn't have great depth constraints, and some recent work on the origins of anisotropy at the Eastern North American margin, some of which I assume I think we'll see later in this meeting. So Brandon Shook, looking at some active source lines, have thrown a wrench into that. They've seen really shallow, strong anisotropy that might be restricted to the lithosphere. This is some work by Josh Russell. We'll also probably see here later, looking at anisotropy offshore of the Eastern North American margin. This is from ambient noise, but we have this strong margin parallel anisotropy. This is for the 20-second period. Again, should be solidly a lithospheric signal. So the question is this margin parallel something locked into the lithosphere and telling us about the initial formation of the margin, or is it really in the asthenospheric mantle and telling us something about the ongoing active dynamics at the margin? Is this something that is being driven by a deep continental keel, by an ocean-continent transition? And this is still sort of ongoing work. So this work by Brandon and Josh suggests it might be lithospheric. This is some work by Brennan Brunswick at UCSB, who is trying to use S-wave body wave tomography while also looking at anisotropy. And his results suggest that most of the anisotropy is restricted at asthenospheric depths. So are we seeing this sort of contribution from the shallow? Is it structural? Is it initial formation? Or is it deeper, and is it active dynamics that we're seeing? So I'm throwing my hat here in this ring as well, and I'm going to use another technique to look at anisotropy. So it's called quasi-love wave scattering. When you have an incoming love wave and it encounters some anisotropic gradient, like we see from strong margin parallel offshore to nearly null onshore, you get a scattering of energy from the love wave onto the Rayleigh wave essentially, and this is called a quasi-love wave. And as you scatter that energy, you can backtrace where that anisotropic scatterer occurred. So the important point for this I want to show now is just that when you have quasi-love scattering, it's a transfer of energy from the love wave onto the Rayleigh wave component. So you can see this on the vertical. And for the OBSs, this is very important because while horizontals tend to be very noisy, we can do these sort of tilt and compliance corrections on the vertical and pull out small signals like a quasi-love wave. So I've been attempting to do this with multiple different frequencies from 50 to 60 seconds, which give us large sensitivity to the lithosphere, all the way out to 100 to 120 seconds, which give us more sensitivities to the asthenosphere. The long story short for here is that at the longer periods, we see very strong scattering right offshore of the Eastern North American margin. This is not really surprising. We see this in the shear wave splitting. We know there's a strong anisotropic gradient there, but we don't see this sort of same cohesive, consistent clustering at these much shorter periods. So this is suggestive here of, sort of a deeper source for this transition in anisotropy. But since this is a marine seismic symposium, I wanted to focus on just some of the observations that we can get from the OBSs themselves. So this is for one earthquake. This is an example of waveforms for one earthquake from the Scotia subduction zone while the Eastern North American Margin community seismic experiment was ongoing. So we have offshore OBS data. This is for the very long period. And so we can actually recover these types of signals after we do a tilt and compliance correction. So the black lines, these are for transportable array stations. This red one, this is a on-land station deployed as part of the community seismic experiment. And we can see the quasi-love wave show up very nicely in these two OBSs offshore. Now this is on its own a very powerful observation, and it's a very important one to make, because when we look at the backscatter locations of our anisotropic gradient, they're relatively diffuse. And this is because we make a very simple, very justified but simple simplification of where to backtrace the source of the scatterer along the ray path. And so we don't know, in this example, is it just onshore, just offshore, where exactly is this boundary? The fact that we can see a quasi-love scatterer on the OBSs means that this is definitively not due to the ocean continent transition, right? The OBS instruments are offshore of the shelf, and so they are not seeing any of sort of the consistent or what we call normal continental interior. So just by having these observations, we know that this is giving us a sense of the gradient further offshore. So this is not the quasi-love scattering we're here to see at the OBSs. This is not due to that transition we saw in the splitting. This can't be due to the transition from margin parallel to null onshore. This is telling us about something further offshore. And if we look at the short period, we can actually continue to see this level of signal. So we can still see quasi-love scattering, especially strongly, surprisingly, for these offshore OBSs. The time delay is relatively short, so this means it's probably further out. But I was shocked when I first saw these. I didn't think we'd be able to see these type of signals. And so, as Sean said in the last session, we were talking about, don't be afraid of the tilt and compliance. Yeah, they can be a pain in the butt, but there are lovely codes out there. And when done correctly, you can actually pull a lot more out of this than I originally thought I could. So I will leave it with that, and just a few caveats here at the end. One problem is, while we can tilt and compliance correct the vertical, the horizontals are too noisy to make us a proper measurement. And I will start the question period for mine with a question to you guys with, how can we make sure that these are not necessarily tilt issues? Anytime we see something that should be a signal that's a scattering, in this case from a horizontal component onto a vertical component, if we don't correctly correct for all of the tilt, this might actually just be love waves bleeding on here. And so this is still something I'm struggling with OBSs. So I will start the session with a question to the group. That's all I got.
All right, thanks Colton for that talk. So questions from the audience, same routine as always, either type it in the chat or raise your hand and wait to be called on. Or we can do the SPAR method of raising your hand in the video.
Easier than pushing the button. That data on the quasi-love wave is amazing. What's the amplitude of those quasi-love waves compared to the Rayleigh wave in sort of percentage?
They're very high, actually. They are nearly, in some cases, even on the land stations, they're nearly about as large as the Rayleigh wave itself. In terms of the love wave, the amplitude on the land stations, because we don't have a great constraint for the OBSs, but it's somewhere around, it's less than 10%.
It seems very difficult to have it be an OBS problem where you'd be rotating a piece of the Rayleigh wave into the Love wave.
Yeah.
The fill corrections, you're basically taking like 1% of the horizontals to correct the verticals.
Yeah, so I agree, but the thing that makes me nervous is because it's a backscatterer, if that scattering point is very near to the station, there's going to be almost no time delay between the Love wave and the quasi-Love wave, which makes me worried even if we're just tilting a little bit of that horizontal energy in there, it's going to look like a quasi-Love wave even if it's still just the Love wave, if that made any sense.
There's some question whether topography with Rayleigh waves traveling perpendicular topography could couple into Love waves.
Yeah.
But, or the other way around, I guess.
Yeah.
Okay, Joe Burns has in the chat, you look to use the shallow broadbands in Alaska quite a bit here. Can you speak to the quality of the shallow water broadbands for splitting? I remember some success with those noisy stations in Cascadia for SKS.
Yes. So in general, my main reference point is the ENAM OBS data. I didn't work with Cascadia, but the AACSE data is a lot noisier on the horizontals than the ENAM was. So even though Eastern North American Margin OBS deployment only had 30 stations, the actually total number of splitting measurements between the two regions didn't vary by that much. There's maybe 20% more total AACSE stations than, or sorry, splitting measurements at AACSE stations compared to ENAM, even though there's more than twice the instruments. So there is a lot of, it's a lot noisier, but in general, I think, there's strong signal there. It's just a matter of, can you get any well-resolved measurement? So the other thing I will note with the broadbands in the shallowest water is, let's see if I can share this quickly. So if we go back to just these orientations that I have calculated for the Alaska experiment, the yellow stations, these are all very shallow water instruments. And so they show the largest amount of disagreement between the orientations from P wave and the orientations from the Rayleigh waves. And this is sort of an interesting pattern because these are done in different frequencies. So that's right there pretty, showing the differences that we have in the different noise character. You can also see from the error bars that in some cases, the error on the P wave is the whole any orientation. So that's the biggest thing that I saw in terms of quality in the shallow OBS instruments. But there's nice, SKS, SKKS, PKS signal on almost every instrument. It's just whether or not we could get the errors to be low enough to give us something that's well resolved.
Okay, any other last questions for Colton before we move on to the next talk? And if not, we can thank Colton again and then move on to the next talk on time. So that'd be great. Okay, and so our final talk for this session is going to be by Jim Garrity, who's a professor at Northern Arizona University. And the title of his talk is New Insights into Continental Rifting from Amphibious Seismic Imaging of the Malawi Rift, East Africa. So Jim, share your screen and take it away.
Thank you, Helen, and thanks to you and Lindsay and everybody else who organized this session. This has been really great today, and I enjoyed both the science talks, and it was fun to have the kind of the technology discussion as well. So this has been a good day. Let me just get this full screen. You guys can see that? Okay. All right, good. Thanks. Yeah, thanks for the opportunity to talk to you guys today. This is it's been a really fun experiment that I'm going to try to run you through quickly. It's there's still some work to do. There's always more work to do. There's a lot of good data here, as you're going to see, but it's a mature project, and so I'm going to try to give you an overview of a lot of the things that have come out, and it's a pretty wide range of activities that took place. It was a big collaborative project, as you're going to see. I just want to highlight here that what I'm going to focus on is primarily the work that we did at Lamont in conjunction with graduate student Natalie Accardo and postdoc Emily Hopper, and then sort of the broader collaborations with the rest of the group, as you're going to see, play really key roles in understanding those studies. But I thought I'd try to highlight the work that Natalie and Emily were leaders on. So if I can, just to start off, I mean, I think we've seen a lot of work along the oceanic margins this morning, and I'm going to jump onto the continent and really focus on the East African rift system and kind of try to emphasize it is just a spectacular example of continental breakup. And obviously continental breakup leads to the continental margins, and that are of interest to a lot of us in a variety of different ways. In detail, if you're not familiar with it, it kind of runs, it's a very active system that runs from, this is the northeastern corner of Africa here, running from the Red Sea system all the way down the east side of Africa. It has really dramatic changes in character along it, with highly volcanic regions, for example, up here in the northern part of the system and the easternmost part of the system. That contrasts really nicely with the kind of what we call the western branch of the rift down here west of the Tanzanian craton and south of the Tanzanian craton, where there's much less magmatism and volcanism involved, but really, really dramatic large-scale faulting systems. And that's going to be the kind of system that we're going to focus on in this talk. In general, for rifting, it's a fairly slow extensional process, as we're going to see. The northern parts are kind of moderately to highly extended. They've been fairly active for maybe close to 50 million years, where the western rift is sort of more weakly extended and it's a little bit earlier in the process. And so what we're going to try to do is really compare both volcanic and non-volcanic parts of these systems and better understand how continental breakup works in a larger framework. And so there's some really basic questions that have been around in our community for a long time in terms of kind of what controls this breakup process. It's important for, say, shallow hazards type processes and resource type processes in terms of what's controlling faulting and basin development and volcanisms near the surface. But those questions clearly then relate to how when you pull on something and extend it, how is that extension accommodated in the bulk of the crust? And then how does that relate to the overall strength of the lithosphere? And that underlying strength of the lithosphere has really been, I think, set up in a lot of ways this paradox or quandary that we've been trying to better understand and address. And that's sort of schematically shown in this kind of classic figure from Roger Buck, where if you basically try to sum up the strength of the overall strength of the crust and lithospheric column, and in a region like Africa where you have a fairly stable cold continental lithosphere, then the strength of that profile is really much stronger than the forces that are available tectonically to try to pull it apart. And so the notion of a weakening process being really critical to this allowing extension to happen at all has been sort of underlying a lot of the work that people have been doing for the last 20 years. And Roger proposed that magmatic diking in particular, the diking processes schematized very simply here, but generally the diking processes, the magma transport processes that are feeding volcanic systems at the surface can significantly reduce the strength of that lithosphere. And so this has been a working model and a working hypothesis that's been at the center of a lot of the work in East Africa and elsewhere to understand rifting processes. And I think one of the caveats to that, though, is not all rifts have very much evidence of pervasive magmatism. And the one we're going to look at is an example of that. So in the magmal pore systems, the questions then become really simple. And I'm sort of just got some really simple ones listed here that we're actually going to try to come back to at the end and address directly. You know, really trying to better document and quantify how is the extension accommodated in the lithosphere through time, and then through that way get a better understanding of what's controlling the strength properties. What is the role of magmatism in magma pore systems? It's not like it necessarily is zero. It just may not be as obvious to us, and that's part of the questions we've been trying to address. And then the last is, you know, may there be a really important role for what we call pre-existing lithospheric structure, which could be any large range of things that could control the fabric and or strength of the lithospheric column before you try to initiate rifting in it. And so those are the kind of the questions that we're going to try to address with what I would argue is a very holistic and classic amphibious experiment that brings in the full range of amphibious imaging opportunities that are available to us. So we're going to focus in on the southernmost portion of the East African Rift System, the Malawi or Nyasa Rift. That was the extension. I should have pointed it out on that initial map. But it is sort of south of the Tanzanian Craton. And it is really a classic fault-dominated, what we would call Western Branch Rift. It's got big, high mountains, Livingstone Mountains, Nika Plateau, that are bounded by very large offset border faults, and that's going to be one of our big targets to better understand the activity on that border fault. Steps to the south, and the border fault changes polarity. So up to the northeast, it's west dipping. To the central, what we call the central basin, it's east dipping. And so that segmentation is a classic example of Western rifts. Extension rates here are about 1 to 3 millimeters per year. Interestingly, and a really nice experiment for us, is it sits very close to, but not directly on, the southernmost extent of volcanism within the East African Rift System. So the Rungwe volcanic province I'll be referring to are these set of volcanoes that are at the northern tip of the Rift Basin. And importantly, we're going to get to back at the end, this inset here sort of shows this crazy color scheme of a bunch of different Proterozoic, primarily, terrains that, in a simplified framework, all represent very old remnants of collisional events that built the African continent, and subduction sutures would be one way you might think about a lot of these terrain boundaries. And so those underlying Paleozoic and Proterozoic continental structures are something that we think may come into and play an important role. And so the system overall really begs for an amphibious approach. It's relatively large scale, but with, for reference here, your latitude line, so there's 100 kilometers. The width of the lake is on the order of 50 kilometers. And so just trying to do an imaging experiment and understanding what's going on in the center of this rift system really requires us to get in the water. But at the same time, getting in the water only shows us a little piece. And so we really need to we really want to try to span the system and understand it at a lithospheric and even into the asthenospheric scale with a fairly holistic perspective. And so to really accomplish that, we undertook a very large collaborative experiment. This was funded by the old Continental Dynamics program, one of the last Continental Dynamics projects. And so it incorporated a wide range of observational tools. It incorporated a wide range of institutions that were involved, both in the US and in our partnership countries in both Malawi on the western side of the lake and Tanzania on the northeastern side of the lake. And I won't go through all the listed names in detail here. Donna Shillington was really instrumental in pulling this together and leading this effort. And but the partnership was very broad and active, and graduate students from all U.S. institutions were heavily engaged in the project, and both in the field and the data collection stage. So shown on this map then are the various elements that we undertook. Sort of the broad background framework is provided by 55 broadband onshore stations that we obtained through Pascal. And those recorded data for on the order of, there was a little bit of a time variability, but on the order of a year and a half or so. And it provided a very nice large scale broadband framework to do our large scale imaging. We included within that 7 broadband OBSs within the lake so that we could keep an instrument spacing of something between 50 and 100 kilometers across the entire imaging zone. And those were important for the passive imaging that I'm going to show you. In addition, we deployed a set of short period OBSs for a classic refraction and reflection experiment, and I'm going to show you some details of that. There are a number of GPS sites that are on here. I'm covering up my corner there. Yeah, the stars there are the GPS sites. Those are actually still ongoing. We've managed to keep little bits of funding associated with this project going long enough that we've been able to continue collection of that data. The rates here are very slow, and so those, not really any significant results have emerged from those yet, but we're hoping that over the course of the next few years, we'll be able to actually quantify deformation in a broader framework geodetically. There was also a really ambitious MT program that has been very difficult to do the data analysis on. It's a highly complex region to image electrically, and so that's analysis is still ongoing. And then there's a geochemical component that I'll tie to a little bit in the end that sampled a lot of the volcanic rocks around Runway to get a better handle on the system in a thermobarometric sense, sort of the temperatures and pressures associated with volcanism in the region. So I'm going to focus mostly on the offshore part, but I thought I'd sort of give you just the little taste of what underlay this onshore component. It was a relatively large-scale experiment to do in an area like East Africa, and so it really took a lot of effort, both from students from the U.S., but also really having tremendously strong partners in Malawi and Tanzania, which we were fortunate to have. But it was a kind of a typical. This is one of the sites in a village in southwest Tanzania, and it really it was kind of a classic Pascal type deployment with broadband systems put in the ground, the communications and solar panels on the roofs nearby to provide security. It provides a pretty noisy data set, and we're going to see a mention of that in a bit. But for the most part, it was a classic bread and butter onshore Pascal experiment that produced a pretty nice data set that we were able to exploit for a variety of studies. The offshore component was somewhat less traditional. It required first acquiring some marine vessels that we could make use of, and so I'm going to show you a little bit more detail on this guy in a second, but basically we had to put together an active source ship that could both handle a large air gun source and the compressors associated with it, combined with the computer equipment to operate that, combined with the ability to tow a streamer. And so that required actually being in country for a couple months, working with marine architects to put that together. And then we made use of some facilities that the Malawian the Malawian Lake Company was able to provide us a fishing research vessel and then ultimately a newer commercial vessel to do some our OBS work. And this basically was effectively using trawling equipment to deploy and recover OBSs. So it was a challenge technically, but really in the end worked out pretty well. So that container ship was set up with this large set of vans on the front and included accommodation space for the scientists and then the workspace. And you can see a streamer reel there, and had to set it up with a system with a crane to deploy the air guns off of the side of the ship. The streamer was a 1,500 meter long streamer that was owned by Syracuse University, Chris Schultz at Syracuse University. We partnered with a group in Denmark to provide primarily the seismic source that we used, and the numbers on that are here. We shot a relatively low volume for the MCS acquisition and then turned up the volume to do the wider angle OBS work. So just a couple pictures real quick of what that looked like. The crane here with the wheels removed was about the only crane we could find in Malawi to do this work, and so they mounted it on the ship for us for a month. So the OBSs the air guns we could lower over the side and tow behind the ship using this kind of ironing board structure here and the crane. The streamer, they were not so lucky. They actually had no mechanism to automatically deploy the streamer. So every time the streamer went out, it was a large streamer party reeling out 1,500 meters of streamer by hand. And Donna can tell you more stories about that if you want to hear. On the OBS side, this was work that I was involved in. We made use of, as I mentioned, the fishing vessel. We deployed pretty heavy broadband systems on that vessel, and so that took a lot of work and planning to make sure that we could do that, but it worked out well. The Scripps group the Scripps OBS group was the group that were willing to take this on with us, and I really, yeah, it's a tough work environment. These ships were not comfortable. There's no air conditioning on this particular vessel, for example, and you're on African Lake in the middle of April. So, yeah, it was great. It was really a pretty tremendous experiment. For the broadband recovery, actually, it turned out that this ship was really going to have trouble with the broadband recoveries, and so thankfully we were able to get use of this commercial vessel to do the recoveries. So the data, just to kind of quickly give you a feel for this and to kind of think about it in this broader holistic environment. Wide angle refraction data shown here, an example OBS, seeing very clear first P wave arrivals through both the sediment parts of the basin, as we're going to see, but also the crustal structure out to a couple hundred kilometers. So this is pretty successful and typical for marine going OBS data sets, even with a fairly modest source like we were using. Here's an example of the MCS data that comes. It's a 1,500 meter streamer, so not quite the quality that you might see from the Langseth, but really useful for characterizing the sediment package. The basins here, as we're going to see, are very, very thick, and so you don't necessarily always get to basement, but there's a lot that we can learn about the faulting processes, as we're going to see with the detailed MCS imaging of the basin. And then here's our broadband array with our limited number of OBSs shown here in red. Really provides a nice, consistent data set to do imaging across the region. The data quality generally was pretty high. And so we were able to make use of a lot of these data for both the body wave and the surface wave analyses. And just kind of like a little couple little points for you data geeks out there that actually work with OBS data. Two interesting things that really came out on this is that, number one, so here's the classic microseismic spectra associated with any seismic data with the high and low noise boundaries in red there. Our OBSs are sort of sitting here. This is one of the onshore stations. And so in our microseism framework, in that microseism window, we have higher noise levels, as we sort of expect to see when we're actually in the water body. We do see infragravity waves within the lake itself, and so that was a really pretty interesting observation. These oceanic microseisms are actually the microseisms propagating across the continents from the ocean. We actually picked up additional microseisms that we've got a paper in preparation for that we're able to look at as well in terms of actual wave activity in the lake. And then the last point I wanted to make is that when people tell you OBSs are noisy, remember that it's always relative to what else you're working with. And so in the high frequency range, in particular for the seismicity studies, the OBSs were much, much quieter than our onshore stations were, because all those onshore stations are sitting in villages and very, very much dominated by cultural noise. So OBS data can be really, really powerful in certain scenarios. All right, so with that data, then, we want to try to put together a pretty holistic view of this continental rift system, and I'm going to step you through this from top to bottom. This is a figure, those of you who saw the introductory talk that Donna gave yesterday, she used as well. And so we're going to look first in sort of the detailed structure of the upper crust and how that is going to better constrain our understanding of how deformation has been localized in the rift system. We're going to then step back and start to bring in some of the passive data combined with some of how to think about things in a little bit of a more crustal architecture scale, and how that can tell us about what is the dominant processes of the rifting. And then we're going to bring in particular, some surface wave constraints that allow us a much broader set of information on really what the state of the mantle is beneath this system, and how that may be influencing the overall extensional processes. So starting at the top, the kind of the active source marine parts of the data. Here's an example of a MCS reflection profile showing two-way travel time, kind of spanning across the rift. We'll dig into this in a second. Really obvious in here, I think, that you can see very large-scale fault structures that are within the basin, and we're going to look at those in some detail. This is a profile that kind of exemplifies the wide-angle tomography analysis that we're using here. Basically a first arrival tomography produces a relatively smooth image, but then we can couple with the MCS image to get a better understanding of what the meaning of some of these offsets are. And this is really going to be very, very important for kind of characterizing the entire basin architecture as a whole, as we're going to see. And this is the work of Natalie, published in 2018, and the MCS work, Donna and Chris published in a couple of the papers just last year. So first, Natalie's model. This is a depth slice at 3.5 kilometers through the north and central basin, and then a couple of cross sections across that. And you see very kind of the dominant thing that you see here that's been critical for our interpretation is a much better understanding of what the large scale basin development is associated with the large border faults. And so if we basically use her velocity models to try to track the base of what we're calling a syn rift, kind of the syn rift basin part of the system, then we can project that as a depth surface on the right there. And you can see that that base of that syn rift system varies from something as deep as about 5 kilometers along the 2 border faults. So nearest the controlling fault systems, and then shallows away from those. So sort of classic half graben structure in each segment. And that the depth is very consistent along there. And so we've really been able to quantify much better than we were able to do previously, really how much extension this is, how localized it is, how much throw there is on these really major fault systems. So if we kind of quantify that in this diagram here and kind of compare the offshore elevation of the profiles as you go along those border fault strikes. So this is south to north, going up the west side of the lake and then transitioning up the northeast side of the lake. There's our elevation profile. And now coinciding with that, we can look at the depth to the basement. And one of the really interesting things we see there is that within the system, the depth to the basement across these 2 border faults is very, very consistent. We've basically piled up something on the close to 5 kilometers of sediment, even across the ends of those faults. And so that suggests that these faults grew very, very early in the rifting process to their current length, and the system extended with those very long faults in place. And that's been a debate within the extensional normal faulting community, is the trade-off between growing normal faults and having them have their length established initially. The second thing we see is we can really quantify how much throw that is. And that's basically the large vertical. It implies we see displacements when we go from the peaks of the elevation to the base of the basements of on the order of 7 kilometers, which imply throws of 8 kilometers. And if we put then the length scales associated with those faults combined with their displacement, these are among the biggest faults, normal faults on the planet. And it's something that maybe was obvious to other people. It was not something that was necessarily obvious to some of us. And so it really, it suggests that these have reached a very, very mature length, and much of the work that's taken in building this basin has taken place through those faults. If you do, there's been some numerical models that have kind of evaluated the relationship between fault throw and fault length, and it suggests, those models would suggest that these faults maybe actually have reached their maturity, and that may be an important constraint on the future evolution of this basement, is that you're not really going to be able to get much more extension on those border faults, and it suggests that other faults are going to have to take a much bigger role. So then, if you look in detail using the reflection data in the basin itself, then you can quantify some of those intrabasin faults as well. We see that we have a very active set of intrabasin faults that not only are offsetting basement, and so have been active over a very long period of time, but also are very active today. And we think that those have taken up something like 20 to 25% of the total displacement, the total extension on the system. So one of the questions would be, if the border faults are starting to shut down, these faults may then become the more active ones to think about, for example, from a hazard standpoint. All right, so at the crustal architecture scale, we sort of are trying to combine 2 things. One is to make use of the wide angle data, and this is still sort of work in progress, as you're gonna see, work that Donna's been working on, but we've got some nice reflections that we would interpret as PMP, for example, that allow us to do a larger scale imaging of the crustal architecture. And we're gonna combine that with classic receiver function observations that we have over this wide array of stations onshore and offshore. And so by bringing those 2 things together, we've sort of developed the inference that there's been relatively localized thinning within the lake itself, crustal thicknesses that are maybe on the order of 32 kilometers or so, 32 to 35. As you step on shore, the thicknesses tend to be a little bit higher than that. And the other thing that really, at least, maybe doesn't jump out at you at first, but I guess the fact that this looks like a scatter shot of colors, there's not really a nicely localized thinning of the crust that we really observe onshore. For the most part, the thinning that we're observing is offshore. We've got up to 7 kilometers of thinning just associated with the basement. The moho depth here suggests a little bit more as well, but it really suggests that at the crustal scale, all the thinning has really been taking place within the lake, kind of the lake framework itself, and hasn't extended in a very wide footprint. So that's kind of quantified in this figure here, where we sort of keep track of crustal thickness and then compare that, if we sort of assume as average standard crustal thickness across the system, how much thinning has taken place in that crust. And it's very localized. And that really contrasts with what we see when we use those receiver functions and step into the lithospheric part of the system. And so this is work from Emily Hopper, and it basically uses S to P receiver functions to try to characterize changes both in the moho structure, which is in red there, but also we see broadly speaking, a change in velocity character from high velocity to low velocity that we've interpreted as effectively a lithosphere-sinosphere boundary. And we see that that boundary is really broadly upwards beneath the lake itself as you step down through these profiles from north to south in the lake. It's a pretty consistent signal. It's a fairly wide signal, and the scale of this is significant. It's several tens of kilometers. So generally much more extension in the lithospheric part of the system in the mantle lithospheric part of the system than the crust. And so that's kind of what's shown here when we compare this sort of the stretching factor that I showed you before for the crust, how much stretching we got in the crust that's very localized. If we compare the stretching that we're seeing in the mantle lithosphere, so just the mantle part of the lithosphere, then we see that it is much, much larger. We're seeing much more thinning of the mantle lithosphere than we are of the crustal part of the system. So to us, that suggests a bottom-up driven process. And so to understand that bottom-up driven process, we've also had to bring in the velocities from the surface waves. And this is the work of Natalie Accardo. We get some really nice surface wave images where we have low velocity regions up here associated with the volcanism, but really pretty modestly low velocities as we move down the rift. And so you can do cross sections across here, and you see sort of what we're interpreting as kind of upwelling of a sinosphere that's very consistent with those lithosphere-sinosphere boundary images. But if we look in detail, the velocities within that system compared to, say, other much hotter rift systems are really not very low. So it's warm, but it's not really hot, and it's certainly not melt rich. And if we do forward calculations, I'm very sorry, I keep hitting my mouse. If we do forward calculations of what we might expect for the temperature conditions associated with those velocities, we see that our rift system here is really well below the solidus that we would expect. And so there's not a lot of melt around to help with this lithospheric thinning and to help with this overall extensional process. But we see a very localized, focused thinning process that is driven from the bottom. So I'm going to jump ahead. This was sort of the summary of bringing all of those things together for this experiment. Going from a nested, detailed study to the larger scale is really what's allowing us to get to an understanding of this problem. Here's our conceptual model for how we think this system really might be working. And the notion here is that we really don't want to have very high temperatures, but we have a very localized deformation process. And so what we've really built this upon is the observation that we have some pre-existing structures here, some former subduction sutures, for example, that presumably have left behind heterogeneity in the lithospheric column. And the notion here is that if you can sort of mobilize some of the low melting temperature fusible elements of that system, then you can quickly heat and weaken the system in such a way that mechanical extension can then run away. And in places where maybe like runway, where this progressed far enough to be able to get decompression melting going, we see a little bit of volcanism at the surface. But for much of the system, that volcanism, that magnetism that's embedded within here peters out and never actually reaches it to the surface. So this is a working hypothesis that allows us to think about the system in this large framework, but it's still something that we need to think about and go on and look in more detail on. So I've got a conclusion slide there. I'm happy to answer questions. I think it's more important to actually reemphasize at the end here, though, just how much work it takes to do these kinds of experiments. And there's a variety of people, the professional people that operate the OBS pools, the partners that we have in the countries that we're working in, that really are critical to making this happen. And we couldn't have done it without them. So thanks for your attention. Sorry I ran over a little bit, but I'm happy to answer questions.
Thanks, Jim. That was great. Any questions from the audience? Either raise your hand. Okay, so Min Chen, do you want to ask your question?
Yes, this is a great talk, and I'm very impressed about all the data that have been collected, especially in Africa, which I think it's extra work to do everything. It's beautiful. And then I still have the same question as if the lithospheric structure beneath the rift zones, as you imaged both with surface wave tomography and also with probably P2S conversion, S2P conversion. This kind of interface that you observed there, it could be LAB or other type of interface, right? It's not conclusive if it is intro lithospheric discontinuity or if it is real LAB, right?
Correct. Yeah, absolutely. And if you look at these images, then there are there's like, the blue things are the negative discontinuities. And so there are clearly other structures that you might also want to think about and interpret. And so we really were driven to our interpretation by the confluence of these images with these images. And these velocities are, as I mentioned, are not super low, but they're on the order of 4.3 or so. And so sort of, it's reasonable to interpret a boundary that's sitting in this between 80 and 100 kilometers within this. So this is the northern basin. Go to this image here from the northern basin, and that's very similar to where we're seeing this boundary. And so in this case, where it correlates with the velocities, we feel pretty comfortable with that. Certainly, there are many, many places in the continents in particular where these kinds of negative discontinuities are observed, and that's not consistent with those with low shear velocities also being associated with them. And so we needed a different interpretation. We could be being fooled by that, but that's kind of I think that's the simplest interpretation we've been going with so far.
Yeah, it is beautiful in terms of it's so symmetric as if it is symmetric thinning. Right, but from your seismic tomography study from the surface wave, that feature is lopsided. It's just from one side.
It is. Yep. That's true.
How do you explain this inconsistency if you do think it is the same thing?
I don't know if we have. I mean, I would argue that we don't have the definitive resolution to say for sure. So a lot of its asymmetry is down here at depth. And so whether this would look like asymmetric or not in the other image, I don't know. There's definitely the lithosphere that you're starting with on this side is different than the lithosphere you're starting with on this side. And so how those two things are actually going to match up in 3D, I think is not something that we're really able to resolve. We're sort of at the edge of our resolution, both in terms of all these gray zones here are places where you don't have the ray path coverage to be able to stack up the S to P converted phases coherently. And so you just are losing resolution out here on the margins of the array. And at the same time, our surface wave constraints, remember that we're trying to do 3D velocity structure within a limited aperture footprint. And so your ability to resolve the edges of that are really quite limited.
Yeah, thank you so much. Thanks.
As Casey pointed out, just to make sure everyone's on the same page, we're going to be kicked off of this in 5 minutes. But so Megan Flanagan, go ahead. But if you get cut off, can follow up later using Pathables. And if anyone else has any additional follow-up questions, can also follow up with one-on-one meetings and Pathables.
Okay, thanks. I'll be quick. Great talk, Jim. I really enjoyed the whole explanation, the whole picture. It's very tidy. Just maybe a little off topic, a question for you and other speakers today on the topic of equity in science and your collaborators in these logistically challenging regions and countries with different economic and cultural histories. I missed one of your first slides in terms of your collaborators. Do you publish with scientists?
Yes, absolutely.
So long term, like what kind of what benefits do you leave behind for your
it's a great question, and it's something that we definitely think about and worry about a lot. And frankly, the success of it varies significantly depending on the institutions you're working with and depending on the countries a little bit. At all papers we published, I have a list that I was trying to post to the chat, but apparently I can't. So I'll try to post it somewhere. Of all the papers that have come out from this, it's on the order of a dozen. Our collaborators in Tanzania and Malawi are full publishing partners on those. Several of them actually contribute to the back and forth associated with the science that goes along with it. We've worked hard. Our partnership in Malawi has been, I would say, quite successful in the context that we've really helped them develop expertise in-house that they've continued to use to, for example, operate a seismic network there that they didn't have before they kind of got involved in this program. There's a workshop for this program that's going to be happening. The last Geoprisms workshop, I think, was funded last spring. It's been delayed, but it's going to be back in probably Malawi, either Malawi or Tanzania, to really make sure that we can continue to have good conversations with the people there. And in Tanzania, the partnerships are both in the Geological Survey and in the university there, and they've remained engaged in the research. And one of the Tanzanian scientists who's at the Geological Survey there started his master's program at Penn State through this program. So it includes some educational components, it includes ongoing science, and it tries to include support as much as we can within, it's an NSF funded project, we can't leave equipment behind, but we try to use our own resources to help them develop equipment capabilities so they can continue to go on and do, for example, monitoring work. So it's been really, I would say, in these two countries, been really pretty successful.
That's great. Thank you.
Okay, so I think with that, since we're about to get cut off, we'll wrap up the session there. Thank you again to all of our speakers and panel members. Excellent session overall, I think. I really enjoyed all of these talks and discussions. And thanks again for all the audience participation in those questions and discussions as well. With that, we will conclude the session and looking forward to continuing to see everyone over the next 2 weeks.
Thanks, Helen.
Thanks, guys. Great session.
Thanks, everybody.
Yeah, more applause, right?